Welcome, everyone. I'm Chris Wojnicki with the Fort Worth Astronomical Society. Um, Tonight we were supposed to have a our first live in-person star party at the Tandy Hills Natural Area. The weather decided not to cooperate, so that was canceled. However, I am still doing the live Meteorite Show. So if you notice that we haven't had any virtual star parties for just over a month, about a month and a half almost, um, we've had some rather wet weather in April here in Texas, and uh, everything's wet. Everything is mud, and the weekends have not been terribly cooperative. So we've had rain, we've had clouds, and just a lack of time. So when it's cloudy, we don't really want to go out, and especially if the clouds are scheduled to come in soon after sunset. So you go out there and you get ready. And then it's kind of a washout. We actually had that happen yesterday at one of our dark sky sites. One of our club members went out and wanted to do some observing, wanted to do some imaging, and the clouds rolled in at sunset and they had to scrub it. So tonight, instead of looking at the stars, looking at galaxies and nebulae with a telescope, instead we're going to talk about meteorites. Specifically, we're going to talk about asteroids, meteoroids, meteors, meteorites, and then we'll actually take a look at some. We'll go into not a whole lot of detail about them, just a general overview. You can get very, very specific, and there are people who spend their entire lives studying just one type of meteorite. But this is kind of an overview. So if you've never seen a meteorite before, if you've never actually gotten to handle one, hopefully when we come back to doing in-person star parties full time, and when we're able to do this more easily, we'll be able to bring out the meteorites. So let's go ahead and start with the presentation and see how well this works. There we go. Okay, so asteroids, meteoroids, meteors, and meteorites. Let's see. So what we're going to talk about is the general overviews, but we're going to get into specifics. So what we're seeing right here is an asteroid on the left, and we can see a meteorite on the ground as it was found in the Sahara. So this is what they look like when they're fresh on the ground, or relatively fresh. Let's try it a different way. There we go. Okay, so asteroids and meteoroids. Asteroids, generally any object generally larger than 1 meter to smaller than a planet. So Ceres was the largest asteroid, but now it's considered a dwarf planet, just a reclassification. Meteoroids are anything smaller than 1 meter. Basically, it's like it's general debris in the solar system, and it's really small. It's very hard to see because of that. So meteor, that's the visible path of a meteoroid as it goes through the atmosphere. Right there. A meteorite is a meteoroid that impacts the ground and survives that impact. We like to call that lithobraking. And the word meteor comes from the ancient Greek word meteoros, which means high in the air. So the Greeks knew that meteors were up high. They just didn't really know how high. So asteroids, large objects, anywhere from a meter to 500 plus kilometers across. The larger asteroids are differentiated just like a planet. So they have a core, a mantle, and a crust. But that means that they're large enough that the impacts as they were forming, easiest way to describe it, as an object falls. No, let me rephrase that. Two objects a certain distance apart have gravitational potential energy. This is the energy of gravity that would bring them together. Okay, we call that potential energy. So as they're moving, that's now the potential energy is being turned into kinetic energy, so the energy of movement. So if you have a large planetoid and a rock that's coming toward it, it has gravitational potential energy because of its position above that planet. As it impacts, it now has kinetic energy, which is, it turned that potential energy into kinetic energy, and now it's hit it. That energy has to go somewhere. So it goes into blasting off material. It goes into melting both the impactor and the impactee. So with larger asteroids during the Great Bombardment period in the formation of our solar system, you had all these rocks just slamming into each other, and that releases energy. It heated up material. In the case of asteroids and planets, it heated up enough that the surfaces were fairly molten. So when you have molten rock, what's going to happen is the lighter stuff is going to float on top, and the denser stuff is going to sink down towards the center, which is what we see with planets and larger asteroids. We see a crust of silicates, which are relatively, excuse me, relatively light, and then you have mantle material, which is a little bit denser, and then you have the core, which is nickel and iron, which is very dense. So asteroids have the same thing. If they're large enough, they have that differentiation. So we see a crust, we see a mantle, and we see a core. If they're smaller, they don't get that differentiation. Instead, the smaller asteroids they're rubble piles, is what we can think of them. Think of it just like a bunch of rocks that are stuck together with gravity. And if you have a large enough impact, it's going to shatter that asteroid. So we've actually visited several that are that small. The OSIRIS-REx probe back in, I think, like 2015, 2014, it visited no, it's more recent. Sorry, I was thinking of a different one. The OSIRIS-REx probe visited a asteroid called Bennu, Bennu, and it is a rubble pile. It's just being held together by gravity, and a strong enough impact from a large enough asteroid will shatter it. So, and many meteorites come from impacts on asteroids. So something hits an asteroid, blasts off pieces, and those pieces go around and around and around, and eventually some of them land on Earth. So, types of asteroids. The C-type asteroids for chondrites, and we'll get into chondrites, they're the most common, and they probably consist mostly of clay and silicates, and they're pretty dark. We think these are some of the most ancient objects in the solar system, some of the earliest to form. We have the stonies, and the stonies are made of a silicate material and some nickel iron. And this is asteroid Ida, so it kind of gives you an image, and it also tells you a bit of the scale, so you can see just how big it actually is. Then we have the metallics, the M types, and these are nickel iron. These, let's see, the asteroid composition, the differences depend partially on how far they form from the sun, and then again with the differentiated ones, because of all those impacts, it heated them up, and we have differentiated crust, mantle, and core materials. But the metallics are kind of interesting because we think the metallics are the remnants of the cores of larger planetoids or differentiated asteroids. So in this case, that iron melts, sinks down to the center, and what bubbles up is the silicates, including in this case the more basaltic lava. Finding asteroids. So the very first asteroid we found was Ceres in 1801. A year later, we found Pallas, then Juno, then Vesta, then Australia. And it took 48 years to find 10 asteroids. By then, people started looking. We also had better equipment, better telescopes, better lenses, better mirrors, larger telescopes, larger mirrors, larger lenses. So we could see more detail, and people were doing observing. But this is still before we started using photographs. So we found 100 asteroids by 1868. And then 1921, we found 1,000. And 10,000 by 1981. But if you look, we jump. In 19 years, we went from 10,000 to 100,000. And then in another 9 years, we jumped up another 400,000. We have, 700,000 by 2015. And when I checked this in January, I don't have latest numbers right now, but this is the number, 995,000 as of January 2021. We've probably blown past 1 million right now. Yeah, easily. but we've got about 25,000 now known Earth-crossing asteroids. What that means is these are asteroids that come close to Earth, specifically that cross our orbit. So if you have a asteroid that's relatively close to Earth, but it never crosses our orbit, it's not really something to worry about. These are ones that cross our orbit, that come close enough that they are a worry. And we do have to pay attention. There was actually something that came out of NASA, I think I saw it a couple days ago, and it was that we would need 3 to 5 years, I think it was. We would need several years advanced warning to be able to deflect a large asteroid. We could not do it within 6 months. If we found something within 6 months, it's going to hit us. There's not much we can do about it. We actually need time. And there's lots of methods to do that, but we're not going to get into all that. This is a neat little video I want to show. And this talks about, now it's a time lapse of discoveries from 1980. Whoops, wrong one. Let's go here. There we go. So this is a time lapse of discoveries from 1980 to today. So the bright dots are the discoveries of asteroids, and then they fade off into the red, the deep red, known asteroids. And you can see as days pass, asteroids are being found. At this time, it's professional astronomers using larger telescopes of meter class and higher with film cameras take the images. You take one image on a clear night, and then the next night you take an image of the same section of the sky and you compare the two. If you see any stars move, you take note, and then you image again on the next available night and see if it moves again. And you keep imaging until you figure out its position. And if you have 3 positions, then you can calculate an orbit. So at this time, amateur astronomers are also finding asteroids through their own film photos or just visual observations. So they're comparing stars in the eyepiece with the star chart, and they're finding differences. It's a challenge even for seasoned visual astronomers, but there are people who do it. So every once in a while we can see like a little burst of activity too, like right there. So these little bursts are asteroid surveys, like right there. They're done as research projects with weeks of observations, and their whole point is to find new asteroids. And then starting about the mid-1990s, we see a speed up of asteroid discoveries for one simple reason: computerization. Automated, computerized telescope mounts started to be developed at a cost point that were reachable for smaller observatories and universities, and with them we had the first CCD cameras. So you can see the numbers. They're about to climb up fast. There we go. Now we can see these. So as we're going, we can see a lot of these surveys being done. Oh, and then you will also see some asteroids way out here. This is Jupiter. So what we're going to see is asteroids out here and asteroids behind Jupiter as well, and then a couple on the exact opposite side of Jupiter. So right there we go. So about this time, we have the cost dropping. So amateur astronomers are starting to get involved with these surveys as well. New, bigger camera chips are expensive, but early adopters like large research observatories, they start to use them for their own surveys, and the older chip prices go down, so amateur astronomers get access to better equipment. We see this continuing even today. So equipment and software in the hands of the average astronomer today can produce images as good or better than those of professional astronomers from 30 years ago, with shorter exposures and less effort. And now in the mid-2000s, we see the start of continuous automated surveys. Computers are starting to compare the images taken day to day and sending hits to astronomers to evaluate. And in a couple more years, in 2010, we'll see something a little bit different. Instead of asteroids being detected just from Earth-based observations, we see satellites like the Canadian Near-Earth Object Surveillance Satellite. With a small telescope, a 6-inch telescope, and a CCD imaging camera, these are able to look for asteroids 24 hours a day for continuous observation, and you can see those sweeps now. And so now we're also seeing the Trojan and the Greek asteroid camps out at the Lagrange 4 and 5 points near Jupiter. The Greeks lead here at Lagrange 4, and the Trojans follow at L5. And on the opposite side, we can't really see here, but where Jupiter is here, on the opposite side, we have the Hilda group of asteroids named after 153 Hilda. And that's at Lagrange, opposite side, at L3. So, and as we close in on today, we see more of these automated surveys and a lot more of these near-Earth asteroids being found. You can see just so many, and night after night after night, we're just constantly seeing more asteroids. We're finding more out there. We're finding them smaller. We're finding them dimmer and darker. And lots of Greeks and lots of Trojans. I don't know if we'll be able to pick out the Hilda group. The Hildas will be right over here. But there we go. That's all the data I have. This is a really neat little video, and you can probably find it online fairly quickly too, if you'd like to see. Going on. So, meteoroids. They're smaller than asteroids, from grains of dust to about a meter in diameter. It's the general space debris around the solar system. These are usually broken pieces of comets or asteroids. They're composed of rock and metal, and they're very difficult to spot before they enter the atmosphere. They're very small. If it's a meter or smaller and they're very dark, how are you going to find it? They don't show up well in telescopes. Radar is another thing. We could use radar to track it, but again, it's very, very small. It's a meter, and we're talking about detecting them at ranges of tens of millions of miles. It is not easy. So typically, we don't even know that they're out there until they hit us. So meteors and meteor showers. Most meteors they're pea-sized to softball, and they burn up completely in the atmosphere. So meteor showers actually come from the debris streams of comets. So as the comet goes around the sun, when it has that tail, that's material that's being pushed off, it's getting blown off of the comet. And it stays in the same general orbit. So you have this stream of particles that follow the orbit of that comet. And when the Earth passes through, we have a meteor shower, or if it's enough of them, we have a meteor storm. So if it's just a few to 1,000 or so meteors, if it's a few to, let's say, 100, 200 per hour, that's a meteor shower. If it gets into thousands or tens of thousands of meteors an hour, that's what we call a meteor storm. I've never seen a meteor storm, but I've seen lots of meteor showers. They're really fun. The best way to observe a meteor shower is not through a telescope. It is to put a lawn chair down or a blanket down on the ground, lie down and look straight up. That's it. That's all you do. And we typically see meteors better after midnight from these showers, because the side of the Earth that's facing the stream now is impacting face on. So we're just getting more per hour at that point. It's all about orbital dynamics and how the Earth moves. But it's typically after midnight that you want to go see a meteor shower to get the best experience, to see the most. And of course, 95% of all meteors come from comets. Okay, meteors enter the atmosphere anywhere from 11 kilometers a second to 72 kilometers a second, depending on their orbit's orientation with the Earth at the time of the capture. If it's coming up from behind and just catching up, the intercept velocity is just going to be lower. If it's almost head-on, it'll be a lot higher. So this is a real-time video of a Perseid meteor. It's about the size of a small marble or a piece of gravel, a centimeter across. In less than a second, it burns up completely into dust. At altitudes about 80 to 120 kilometers. It's 50 miles, 75 miles up. And that's really important, so I want you to remember that. 50 miles to 75 miles up that meteors are burning. Okay? So this is very small, but it burns so brightly that you can easily see it from 50 plus miles away. Okay? And then fireballs, let's see, is that the right one? Yeah, there we go. Okay, so fireballs are very bright meteors. They're brighter than Venus. Some fireballs can last a few seconds, and they can be various colors depending on the composition. And as they slow down, larger ones can break off pieces like this one, and they just break off and burn separately. Then we have the bolides. So bolides are large fireballs that explode or they break up in the atmosphere. Air gets into cracks and holes on them, and the material just isn't strong enough to withstand the force. So it breaks up into pieces or it explodes. And bolides are small asteroids that enter the atmosphere, and they can typically last just a couple seconds, or several seconds, I should say. There have been several which lasted. Oh, there was one in 1966, I believe. It passed over the United States, and it took 20 something seconds to 30 seconds to cross. This one actually skimmed the atmosphere. It hit the top of the atmosphere, burned up a little bit, slowed down a bit, but then kept going. It missed the Earth. And it was a good thing, too. Then we have Chelyabinsk, the Chelyabinsk super bolide. So this is the one that exploded over Russia just over 8 years ago now. And the entire event, from the first brightening as it entered the atmosphere to the final shatter, explosion, and fade, took 15 seconds. That's it. So this video we're about to see this is taking about 100 miles away from the ground track. The trail is very low on the horizon, but it's still incredibly bright. So this one was between 17 and 20 meters in diameter, call it about the size of a school bus, and it weighed about 10,000 tons. The estimate that this final explosion is about a 500 kiloton TNT airburst. So let's go ahead and take a look at it. Remember, 15 seconds start to finish. We see it brightening. It's coming in. And now we have some explosions right there. And then we have a big one and little pieces falling. And that's it. So the big explosion, actually, there were several here. There's one over here, several through here, and then the big one here. Let's watch it again. It's only 15 seconds. So it's coming in. It's coming in at a fairly low angle, too. So it's going through a lot of atmosphere to slow down. And it explodes. And bits and pieces are now coming down. You can see it stops the fade there. And you would think it kept traveling and landed somewhere over here. But it didn't. In fact, it landed pretty much directly underneath where it stopped. And we'll get into why. So the shock wave from the explosion took about 2 minutes to reach the surface at Chelyabinsk, shattered windows all over the city, partially collapsed one warehouse. Over 7,200 buildings were damaged, mostly glass, just in Chelyabinsk. And there were about 1,500 people who sought medical attention for injuries. There were no deaths, but there were a lot of people who had cuts from glass. So let's talk about this is one on the ice. This is a little fragment on the ice. This is a larger cut piece, and this is the trail after, I think, like another minute or two. So this animation shows just how high this was where it exploded. So it comes in over 80 kilometers high. We see the trail, and we see the explosion, and then so the explosion is about 30 kilometers up or so, and then the rest of it just falls down. Again, I'm going to show it again. I think it'll loop. There we go. So again, as it comes in, it's hitting the top of the atmosphere, 100 kilometers up or so, and then starts to burn up. Pretty bright, keeps going, keeps going. Gets into the mesosphere, and now it's quite bright. When it hits roughly the top of the stratosphere here, it's now encountering a lot of air, a lot of resistance, and that's the point where it explodes. So it's still exploding between 30, 40 kilometers up, and then bits and pieces are falling down. So by the time it hits the troposphere, where all our weather is, it's just rocks falling down. So we see it come in at this very, very shallow angle, and it takes a while to go through this. If it had come straight down or even a steeper angle, it could have very easily hit the ground. Just hit the ground in a larger piece and caused a crater instead of exploding up high and just raining rocks down. So on the average, about 150 tons or so of material falls on the Earth every single day. Most of it's small. It burns up completely into dust in the atmosphere, or it's going to fall into the ocean. It's because, well, 70% of the Earth is covered by ocean. So that's where they end up. And the rest is found in places where you can spot them fairly easily. Deserts are the best place to look for meteorites, and we'll get into why. Oh, and I also should say, if you have any questions, go ahead and put them in the chat. I will be glancing over and seeing if anyone has any questions, any comments, any concerns, and we'll go ahead and answer them as soon as I see them. So we have meteorite falls and we have meteorite finds. And the difference is a fall is an observed event. It's a fireball or a bolide that's tracked, and then fresh meteorites are found where they're expected, and it's called a strewn field. Meteorite finds, these are just meteorites they're just found on the ground. We don't know when they fell. It could have been months, years, centuries. There have actually been meteorites that were found, I think, was it tens of thousands of years after they landed. I think there's one or two that are several million years old, if I recall. But I can't remember which ones they are off the top of my head. And these pictures are courtesy of Tomasz Jakubowski and Marcin Cymala. These are two Polish meteorite hunters and dealers, and I've had an opportunity to talk to both of them. I have pieces from both of them. They're really, really nice guys, and they actually do expeditions out to Northwest Africa, to Morocco, and they look for meteorites. So these are some of their images. And if you would like to purchase meteorites, I don't have any for sale. These are mine. I just like to collect. I just think they're interesting. But I'll go ahead and put in the links for their websites if you're interested in the comments later on the video, or in the description of the video. So what do meteorites look like in the wild? Well, when we find meteorites in the field, we notice them because they don't look like they belong. They stand out from all the other rocks nearby. And the deserts of Northwest Africa are a really good place to look for meteorites. The wind blows the surface sand and dust away, so it leaves what's called desert pavement. It's these little rocks on the surface, and it's got compacted rocks and sand underneath, but it's hard enough they can easily drive on it. And people do. They'll take the probably a Toyota Hilux, and what Marcin and Tomasz will do is they'll actually go out and spend like 2-3 weeks out in the field driving around looking for meteorites. And this is what they're looking for. They're looking for these dark rocks sitting on light colored sand or gravel, stuff that doesn't look like it belongs. Oops, one more. Let's see, what else was it? Oh, so if you look at them, they have got that dark surface on them, and we call this the fusion crust. They don't look like the surrounding rocks. They're a lot lighter in color, so these dark meteorites really stand out, and they're visible even from a distance. So as they're driving along, they're looking out to either side and ahead and seeing, do we see any dark rocks out there? And if they are, they'll just turn over and mark the position of where they are and start cataloging. So if you notice, the exact location on these meteorites has been marked out, and the reason is they have places where they like to go, and they don't necessarily want everybody to know where that is. So that's why that's done. But in the official logs, they know exactly where it is. And if you start looking for these meteorites online, there's actually a meteorite catalog. And it gives the location, the approximate location of where it was found. So it was in this part of Morocco, let's say, and not this part of Morocco, or it's in southern Algeria, or if it's way out in the middle of nowhere. So if you look at these, and remember, these have not been touched, so they're on the ground as they were found. They're not in craters. So by the time these things impact the ground, they're only traveling about 300 to 650 kilometers an hour, or about 190 to 400 miles an hour. Basically, they've shed their speed, and they've ablated off 95% of their mass or so. and that created the fusion crust. What that means is as it goes through the atmosphere, it's the material is being blown off, and that's the ablation. And that ablation is taking the heat away from the rock that remains. And that last little bit is the fusion crust, the last little bit that doesn't get ablated away. So by the time they hit the ground, they're just traveling at terminal velocity. So just like any rock, falling from high. So these aren't big enough to cause craters. They'll just hit the ground, and a little bit of sand dust will pop out, depending on where they're landing. Sometimes not even that. They're just there. So let's see. Oh, and also, meteorite that impacts the ground, it nearly instantly freezes over, it frosts over. It's because the interior is still the same temperature as space. So the passage of the atmosphere is so fast, and the ablation is taking the heat away from the rock. The inside doesn't have time to heat up. So there's no fire, there's no smoke when it impacts. It's a Hollywood effect just to make things more dramatic. When a small meteorite hits the ground, it's cold. It just plops down and it frosts over. So if you ever do see a meteorite land directly in front of you, don't touch it, especially if it's a bit frosty. Give it an hour, let it warm up. It'll be fine. So if you do touch it, you're probably going to get some severe cold burns or frostbite. So if you ever put your tongue on a flagpole on a really cold, freezing winter day, yeah, it's like that, but a lot worse. So don't do it. Not that anyone is likely. I don't know if anyone has ever. No, I take that back. There have been cases of people seeing meteorites land. In one case, I believe in the 60s or 70s, one crashed through the roof of a house, bounced off the floor, and hit a woman in the thigh, leaving a nice big bruise. So it hurt her, but other than that, nothing. There was also a case, there is a record from ancient Egypt of a meteorite falling from the sky, hitting a dog and killing it. Those are the only two that I can recall where it actually hit somebody or something living that was actually recorded. So let's go into classification categories. So we can categorize meteorites one of two ways. The first way is primitive material versus processed material. And before I go on, I don't see any questions yet. All right. Hoping the stream is going okay. If there are any issues, just please go ahead and let me know. We'll do the best we can. Let's see. Okay, primitive material versus processed material. And what does that mean? Primitive material is stuff that's basically been unchanged since the formation of the solar system. It's the oldest material in the solar system and includes chondrites, which are rocks composed of little chondrules, and chondrules are these little bitty droplets of melted material that's the same stuff as the original dust and gas of the early solar system. And then we have the processed material. So the processed material was part of a planet or is an asteroid. It was heated, it was melted, it's changed in any number of ways. It can tell us a lot about where it came from, but it's a lot younger than the rest of the solar system. So primitive meteorites are remnants of the original solar nebula, and different types condense at different distances from the sun, and all depending on the temperature. So stony chondrites formed at and around the distance of the asteroid belt, while the carbonaceous chondrites formed further out than the asteroid belt. And primitive meteorites give us a glimpse into the conditions, the compositions of the early solar system. So that's why they're important. Then we have the processed material. So processed material comes from bigger objects in the solar system. It comes from planets, dwarf planets, and asteroids, that they were big enough to be differentiated with a crust, a mantle, and a core. And pieces knocked off these objects were modified from their original form, usually from melting. And metallic meteorites, like this one in the image, these are the fragments of cores of large differentiated asteroids that were blown apart in collisions. and more processed material. There's other meteorites are pieces of crust material from asteroids from Mars and the Moon and knocked off by impacts. The rocks traveled around and around the solar system and eventually landed on the Earth. Achondrites, they're just silicates without chondrites. So it's crustal material from lunar Martian meteorites and the head group from Vesta. The head group we just call HED head because it's howardites, eucrites, and diogenites. There's 3 different types of material. It's just the head group, just easier. So the nickel iron meteorites come from the cores of big asteroids, and pallasites come from the boundary layer where the mantle of an asteroid kind of meets the molten core. We'll get into that too. Mesositerites are kind of interesting. We think they're from, they're pretty old material. We think they're from the period of the planetary formation. And we think they're created by low velocity collisions of large metallic fragments with the surface of a differentiated asteroid-sized body. So the collisions kind of turned mantle and crust into little bitty like silicate fragments, but left the cores in the form of large, durable chunks of metal, and they just kind of fused into a single mass. And we'll get into mesositerites as well. So what do chondrites tell us? So this is the primitive material again. These are some of the oldest, most similar material to the early solar system. So with these, 20 to 80% of the mass of a chondrite is this spherical millimeter scale little balls called chondrules, and they're scattered throughout the whole matrix that holds it together. So these little dots all through here that you can see, these are the chondrules. And in in zero gravity, liquids tend to form spheres. So we think these were little molten droplets at some point when they first condensed out of the origin nebula, and then they melted. So they formed little spheres, and then they kind of froze up, and eventually were sucked all together into these larger rocks. So when we compare the ratios of elements in the chondrites, specifically the chondrules, they match really closely to what we find in the sun's atmosphere. So we see a lot of chondrites with shock features too, which we think they're from asteroid collisions. So we only have a few that we would consider pristine, but those are really, really important for finding out about the early solar system. Achondrites are silicates from the Moon, Mars, or Vesta. So we have one meteorite which may be from Mercury. This is Northwest Africa, 7325. But we can't really know for sure because there's kind of disagreement on what exactly the chemical signature of a Mercurian meteorite would be. And we don't have any Venusian meteorites because there are 2 factors with that. One, Venus has a pretty high escape velocity, close to what Earth has. And also it has a very, very thick atmosphere that would cause significant drag. So you would have to have a very large impact that would blow off pieces at very high speeds, but high enough too that it would pass through the atmosphere and not be slowed down enough to still maintain escape velocity. So we have no known Venusian meteorites. So most of what we have is lunar and Mars. Again, this is orbital dynamics. So I think what was it? It would take the escape velocity from Mercury. I think was something like it would take something 11 kilometers a second going out in order to potentially reach Earth's orbit. But stuff from Mars would, I think it's like 3.6 kilometers a second to escape from Mars and reach Earth orbit. It's a whole lot less energy. So we have not lots, but we have many Martian meteorites, and we have one maybe Mercurian meteorite. And with Venus, it's kind of the same issue. I think the escape velocity is even higher, the energy requirements, just because of the size of Venus and also the drag. I don't have the numbers off the top of my head. I just remembered Mercury for some reason. So, all right. We also have the primitive achondrites, which we think they're recrystallized chondrites, or some that contain relic chondrules that were partially melted within a few years after the formation of the solar system. So again, old stuff, but not exactly. It's not from early solar system. It's still early. It's not that early. So what do achondrites tell us? These are rock samples from various objects in the solar system, and it tells about the rocks on these bodies. So most of what we have is from, we now think there are two massive collisions on from Vesta. And these are the Howardites, the Eucrites, and the Diogenites. Again, we'll get into them. The other method of categorizing meteorites is stonies, irons, and stony irons. And let me check the questions. Let's see. Okay, let's see. All right. So don't have any questions yet, but again, if you have any questions, go ahead and put it in the chat, and I'm glancing over every once in a while on yet another screen here in my little studio, and I'll answer them as best I can. So here we go. Let's get into this methodology here. Okay, so stonies. Stony meteorites include the chondrites and the achondrites. These are stony meteorites, are mostly silicate rock, and they have small amounts of iron in them for the chondrites, but little to nothing for the achondrites. And 86%, around 86% of all meteorites are stonies. So they are by far the most common. And then we have the carbonaceous chondrites. These are the oldest and the rarest chondrites, forming out past the asteroid belt, where it was colder and allowed the carbon compounds to basically come out of vapor. So they contain complex organic molecules, including amino acids, fatty acids, and other so-called building blocks of life. And we also have the idea of panspermia. So it's the hypothesis that life, or at least the building blocks of life, originated in space and fell to Earth in the form of carbonaceous chondrites. We also have things called calcium aluminum inclusions, and these are some pretty small, millimeter to centimeter scale flecks in carbonaceous chondrites that are the first solids to condense out of the protoplanetary disk. So when we date them using the lead-lead isotope dating system, we can get an absolute age of 4,567,300,000 years, plus or minus about 160,000 years. And we call this Cal times 0, and we use that as the beginning of the formation of the solar system. We used to think that Cals were material that was formed in a supernova. And actually, I had been using this explanation before when I was doing talks on meteorites, and specifically on Cals. And it turns out that's not true. We've had some recent studies of Cals in meteorites, and the isotope ratios are they basically match what we see in the sun and in other early solar system time capsules of meteorites. If they formed in a supernova, the isotope ratios would most likely be different, because because basically the isotope ratios in that star, which collapsed and exploded, would have been different, because that star came out of a different gas cloud, a different nebula than our star did. And different nebulas have different composition, different ratios of isotopes. So we can actually figure out which stars are siblings, which stars came from the same origin nebula by looking at these isotope ratios. And we've had some recent studies that now scientists think that the calcium aluminum inclusions are actually from our origin nebula, from the protoplanetary disk as it was forming. They are not evidence of a nearby supernova explosion. So I always try to be as accurate as I can. If I find that something I thought was true turned out not to be true, I have to change what I think about that. I would rather be right than have a nice story. And the story that a supernova exploded and sent these pieces into our origin nebula along with a shock wave. And these are remnants of the supernova which created our solar system. That's a great story. It just turns out that's not true. So again, I would rather be right than have a happy little story. So I found out by reading some of these studies recently that I was wrong, and scientists were wrong when they thought this before. So this is what it actually is. It is still incredibly interesting because now we have something, the very first stuff to come out of that nebula, the stuff that condensed the first solid material bigger than little pieces of dust. We can still see these in these carbonaceous meteorites, and some carbonaceous meteorites, not all. All right, let's go on. So ordinary chondrites make about 80% of all meteorites. I'll call about 80%, but they're probably not representative of all asteroids. We think about 40% of them come from one specific asteroid, Bosnemakova, but we're not sure. Okay, we think that, and the way we do that is we can actually analyze, and we'll actually get into that in just a bit too. We can actually analyze the material on the surface of these asteroids using spectral analysis, spectroscopy, and we can tell what minerals are on there, and then we can compare it to the meteorite we actually have in hand. The H chondrites, which is just a type of chondrite, it comes from Hebe. The OCs, we think they come from Ida, and the L chondrites, we think come from Eros Flora, and there's like a whole family. They're called the Flora family of asteroids because we think they came from the same parent body. They just got blasted apart because they all have very similar compositions. The LL chondrites, like Chelyabinsk, we think come from Itokawa, which is this asteroid right here. And again, it's all spectral analysis. We're actually looking at these asteroids. We're seeing the light from them, and we're running it through basically a spectrograph. Basically, it's a very, very sensitive camera that just looks at the light and not really a picture of it, and just comparing it to the rocks that we have here on hand. Okay. Achondrites from Mars. So the reason why we know they're from Mars is because they have the same elements in a little bit of inclusions and isotope ratios as the Martian atmosphere. So we've actually sent probes to Mars. We know what the Martian atmosphere is like. We know what the ratio of isotopes on Mars is, and we can compare it to rocks that we have here. So we can say these match up with the data we have from Mars. Therefore, we think that, yes, these are Martian meteorites. And achondrites from the moon, we had astronauts bring back moon samples from several regions, lots of different types of rocks. And some of these achondrites match the rock types exactly. And we'll see some of those too. Okay, achondrites from Vesta. So we think they're from at least one impact, probably two, and that these were large enough to blow off massive chunks to the point where we actually have a group of asteroids called the V-types because these are pieces of Vesta. Check if I have any questions. No questions yet. All right. So we had these impacts that came in. They blasted deep gouges into Vesta. And if you're interested, take a look at some of the videos from the Dawn mission, DAWN, that NASA did in the early 2010s. This was a mission that specifically went to Vesta and I think another asteroid, and it mapped it. It did a lot of orbits, and it was looking at the surface, and it was doing spectroscopy on it to see what minerals are on the surface. It didn't land. Didn't need to. This is this is remote sensing at its best, and it's close up. So what we have is these impacts that gouged out huge chunks of Vesta. The Howardites are stuff which is a crustal material. The Eucrites, they're magma material from the mantle. Basically, they're volcanic. Okay, but it's like magma material that cooled down below the surface. It wasn't a volcano that exploded out like a like a silicate volcano on Earth. Think of it more like almost like a Hawaiian style of volcano where you have basaltic lavas which come up, or basaltic magma which comes up slowly. There's very little to no gas in them, and in this case, they're just upwellings, and and they cool down below the surface, not erupting into outside of the crust, probably. And then we have diogenites. So diogenites are really interesting because these things are from deep in the mantle. So if you think about it, with the Earth, we have to drill down just in the ocean. What is it, like 20 something, 20 kilometers? I think it's like 11 to 15 miles. And that's in the deepest ocean. We have to drill down that deep through crust to reach upper mantle material at the moho layer, or the moho, the boundary between the crust and the mantle. This, we actually have mantle material. We have diogenites from the upper mantle, and we have the olivine rich diogenites from deeper mantle. Not very, very deep down the core, but it's fairly deep. And this is material that we otherwise wouldn't have. We don't have a way of digging into a large asteroid. We barely are able to land on an asteroid at this point and grab a few samples. So this is really, really interesting that we can get this kind of stuff and get this type of sample, that we can recognize what this is and study it. All right, nickel iron. Nickel irons, they come from the cores of large differentiated asteroids that broke up. So the lines that you see on here, they're called Winmanstatten patterns. They're crystals of nickel iron. So when you take an iron meteorite and you slice it and you polish it up a bit, and then you treat it with a little bit of nitric acid to remove some surface oxidation, and that brings out this interleaving. It's a kamacite and tannite bands. They become visible, and now you can see them. These are basically crystals of nickel iron alloys. So the structures can only be seen under really specific circumstances. You have to cool these things down over millions of years, slowly, very, very slowly. So you could only do this in the core of a large asteroid, where the entire asteroid is slowly cooling down, and it's being insulated by the mantle and the crust. There's no way that we can replicate this on Earth in a lab. So this is actually a really good test to see if the lump of iron that you have is meteoritic. You slice it, you polish it, you treat it with nitric acid, and then you wash it off very quickly. And there. So you see these patterns. And it's not always like this. I actually have one that looks like this, and I have one that looks totally different. Several that look totally different. It just depends on, actually on several factors. It depends on how slowly it cooled down, how long it took to cool down. It depends on the exact ratios of nickel to iron. So like with kamacite, it can be anywhere from like 5 to 15% nickel, and then with the tannite, I think it's like up to, let's have to 50% nickel, maybe even higher than that. Let's see, any questions? No questions yet. Okay. So again, we can't replicate this, but if we see it, we know this is definitely meteoritic. And what's interesting is these nickel iron meteorites. These are the sources of the first iron that humans ever worked. If you Google, you look up Tutankhamun's dagger, you'll see it has an iron blade, and gold and jewels on the hilt. At that time, iron was much more expensive than gold. And only a pharaoh would have an iron weapon like that. There's also a large, oh, now I can't remember the name. I can't remember the name. There was a large asteroid. Oh, sorry. There was a large meteorite in Greenland that the Inuit used for centuries as an iron mine. And it was a big iron nickel meteorite just out there near the coast. And what the Inuit did is, well, they did something called cold forging because, frankly, there are no trees in Greenland, no matter what Leif Erikson bragged about when he went back home. So Greenland has no trees. It doesn't really have a way that you can make a fire hot enough to melt iron. So instead, what the Inuit did is they basically took rocks, a big hammerstone, and they hit the iron over and over and over again until they could knock pieces off. Then they took the pieces with the hammerstone again on an anvil stone and beat it thin, folded it over, beat it in a process called cold forging to make spear tips, to make harpoon tips, to make knives, to make whatever tools they needed to survive. And then there was, oh, I can't remember, it was Admiral Perry. I don't remember who it was now off the top of my head. There was an explorer who found it and thought it was really, really neat. So probably not Admiral Perry. I think he was British because he took it back to England, and the Inuit lost their source of iron. They had used it for centuries and barely made a dent in it because the thing weighed several tons. It's just a big hunk of iron. Go on. Stony irons. So stony irons are a mix of silicates and iron nickel. So the two that we typically see, they're the mesositerites and the pallasites. So again, we think the mesositerites, they're low-speed collisions between silicate asteroids and iron cores of broken up differentiated asteroids. It's like a slow-speed collision, just kind of merged all that stuff together. So the image here you see is of a mesositerite. And then we have the pallasites. So pallasites, they're olivine crystals in a iron matrix. And these form in the interface boundary between the molten core of the asteroid and the bottom of the mantle. So where those two kind of meet and start to intermingle, this is where you see the pallasites. And they really are the prettiest of all the meteorites. They're just lovely to look at. With this one here, the trick is they don't look this good if you just cut one in half. It doesn't look this good. You have to polish it up really nice, and you have to cut it super, super thin in order for the what you want is a light shining from behind to shine through the olivine, or olivine is just peridot crystals, peridot gems, basically. So you want the light shining through the olivine, and then the metal blocks it, and you get that lovely orange-yellow color. But you have to slice it super thin. The problem with slicing it super thin is these things are delicate. I have one. It's falling apart. Because someone, name names, somebody was holding it and kind of bending it to see what it could do, because it's metal, right? Yeah, he broke it. So I got a little corner of it which broke off. It happens, so I'm not terribly worried. It's just one of those things. Okay, why are meteorites important? They're really, really important in order so that we can study the solar system. So meteorites from specific locations like the moon, Mars, or asteroids, they tell us about those objects, those worlds. And it's a free sample return mission. You get something from there, but it's going to be pretty random. You don't know what you're going to get. Just luck of the draw. The chondrites and the primitive achondrites, they're time capsules from the early solar system. Those tell us what the solar system was like before it was a solar system, when it was a protoplanetary disk. So it's early, early stuff. So finding out the source of meteorites. How do we know where they actually come from? Actually, before I do that, any questions? No questions. So again, if you have any questions, We can all save them till later. All the same to me. All good. How do we know where the meteorites come from? So we can analyze light reflecting from the asteroids and figure out the composition. So different minerals reflect light differently. So if you have a sensitive enough instrument camera, you can graph the reflectance versus the wavelength, and you get a chart like this. You do the same with the meteorites in the lab because you have them on hand and it's quite easy to do, and then you compare the results. So in this case, we have a carbonaceous chondrite called Renazzo. It's found in Italy in 1824. And then we have the asteroid Pallas. So the plots are very, very similar. So tentatively, we say that Renazzo's parent asteroid is to Pallas. Now, we're not 100% positive unless we go to Pallas, we pick up a rock, and we look at Renazzo. It's like, yeah, these are the same thing. At that point, we can be very certain. But again, probably not 100% certain because Pallas may be the parent of another asteroid, pieces of it that broke off, and Renazzo may have come from that asteroid instead, which it still comes back to Pallas, but now it's a technicality. Nonetheless, this is what we do to find out where meteorites come from. Okay. And then when we did the Dawn mission with Vesta, we did the same thing, except that we had a very close probe that was able to map it and figure out what minerals were on the surface and from where. And what minerals were on the surface, and then compare those to the stuff that we had here. Okay. Meteorite hunting. So the American Meteor Society, they track fireballs and bolides from around the world. So if you have a video you've taken of a meteor, bolide coming down, big old fireball, you can submit it to their database. You can send them videos, and the more observations they have, the more accurate that the track becomes. So this is from one in Missouri from a couple years ago that I've gone on here. And below you can see doorbell cams. Doorbell cams, and there's mostly doorbell cams, and there's one dash cam. So when you have lots of cameras recording, you can pick up stuff like this. And if you know the direction you're heading or what direction the doorbell cam is pointing, you know its field of view, you can calculate how high up in the sky it is, what direction, what time. It just gives you that additional bit of data. So using that, they can plot it and come up with a map on just where it was. So right now we're looking at, let's see, yeah, we're looking at the ground track. So once a track is calculated from the observations, you can figure out where the strew field might be. And the strew field is the area on the map where the fragments may have landed, okay, potentially. So looking at this map, oh, excuse me, I'm going to take a drink. No questions? No questions yet. Okay. So looking at the map, you may think the strew field is going to be right around Rush Hill. But that may not be the case at all. So remember that the meteors are high up in the atmosphere. The line here is the visible part of the track. So about 50-something miles or so long in Missouri. It's projected down onto the surface. The red point is where it stopped being visible. It's not where it landed. So by the time it stopped being visible, it slowed down to only a few hundred miles per hour. And it's probably going ballistic. So if there are winds, they will push it in some direction. And remember, winds can vary in intensity and direction at different altitudes. So if you have a high-level wind from the west, it might push it back towards Middletown. But a strong warm front from the south at lower altitudes could push it north again. Oop. Wrong button. So depending on the winds, it could be anywhere in a circle like this. So I believe it's about two miles or so from Ladonia to here. So somewhere, there's a couple of miles. So if you're talking about a potential strew field that big, that's still going to be several, 20, yeah, about 20 or so square miles. It's a good position. So, sorry, it's a good size strew field. And if this isn't a very large one, if it's not a very bright one, especially out here, this is farmland. And it's not going to be easy to find anything out there. I don't know if anyone found anything from this one. But who knows? So let's see what meteorite hunting is more like. Okay, so the best places to find meteorites. Where do they stand out? So meteorites are dark, so you want to go someplace where they're going to be obvious. Rocky deserts, Antarctica, Greenland, good places to start looking. Sandy deserts tend to swallow meteorites. So they get covered over and disappear under the sand and dust. And, if it lands in a dune field, it's going to get covered up relatively quickly. So we don't go to those places typically, unless we actually saw it come down to that area, if that's possible strew field. So forests and farmlands like Missouri, they're bad places to look for meteorites. So if a rock falls in the forest, does anyone see it? Maybe the bears. If you're walking in the forest and you notice a dark rock sitting under a tree as you walk by, would you think anything of it? No, just dark rock? Probably not. So what if you find dark rock out in the cornfield? Again, same thing. Unless you are expecting it there, it's going to be something you overlook because you're not thinking in those terms of, I'm looking for a meteorite. You've got to be actively hunting for one. But in grass fields and cornfields, any type of farmland, rich soil is dark. So if a dark rock lands in dark soil, you're probably not going to find it. If a rock lands in a cornfield that's just about ready for harvest, you're not going to find it. If it lands in a grassland, in the prairies where you have, grass up to your waist or higher, probably not going to find it either. So we look in places where we can. Now, I say that, but if you know the meteorite is there, you can go look for it. So, excuse me. If it's underground, you can use ground penetrating radar or magnetometer or something else, if it's an iron meteorite, to go look for it. So there's a meteorite called Brenham. This is a palisite from Kansas, and the strew field is in corn. They're cornfields out there. Corn and wheat, I think. So the Fort Worth Museum of Natural History has a fragment of the Brenham palisite in the entryway to the Noble Planetarium. And it's a big heavy rock. And it was found deep underground in a cornfield, and they used instruments to detect the iron to find out where it was. And they came in with a backhoe and dug it out. So they knew about the Brenham strew field. There are other meteorites from this same asteroid that came down. So they knew where to look, and they had suspicions that it was in this field. They just didn't know where. So they had to survey the entire field, figure out where it was, and then come with the backhoe and dig it up. But randomly searching for meteorites in cornfields, it's not going to get you very far. So I don't recommend it. And yeah, so deserts, Antarctica, Greenland. So only under specific circumstances would you look in a forest and grasslands or lakes for meteorites, and that's if you actually saw land there. But here's the thing. If you see a big splash in a lake, is it a meteorite or is it a fish? And it's probably a lot more likely to be a fish. And yeah, don't even think about going through your backyard and finding meteorites. Just don't. And don't bring me rocks that you found in your backyard thinking they're meteorites. I don't want to see those either, because they're not. Okay, instead, a really good place to look for meteorites is Antarctica. A dark rock on the ice really, really stands out. It just doesn't belong there, so it's really obvious. And also, the movement of the ice for the glaciers, it takes meteorites and actually deposits them in big bunches at the edge of the ice. And some of the places in Antarctica, there's the Frontier Mountains, meteorite traps, and then there's the Allen Hills site. Allen Hills has produced a lot of really, really good finds. If you remember from there's the Martian meteorite that was found there that had the potential microfossils back from, I think, like the late early 2000s or so. That was found in Allen Hills. So in these images below, on the image in the left, every one of those little red flags is a potential meteorite. So when people go out to do the surveys and they find a rock that doesn't match, it looks like a meteorite, looks like it has that dark coating, the fusion crust on the outside. It doesn't match any of the rocks there. They'll just put a little flag on it, and then it'll go on. It's much easier to survey it first, mark off all the potential meteorites, and then come back around and do individual surveys of each one. And what they'll do is they'll actually take, they'll go to each one, they'll photograph it in its place without touching it, they'll mark its exact location on GPS, and it'll get some catalog number temporarily for the survey. Then it's bagged up, labeled, toss it in the bin, and keep on going. So with that number, they can track exactly where it was, who found it, and all that other information. And then you analyze it later. You just want to pick them up, but you want to get as much data as you can. And getting photographs and the exact location on GPS on where it was found is really, really important for documentation purposes. Okay, did I find a meteorite? Yeah, probably not. So, let's go over what a meteorite's physical characteristics are. Does it have a dark fusion crust, that shiny, smooth surface on the outside? Maybe. If it doesn't, it could be a... See, here's the thing. The stuff which is a meteorite that doesn't have this is so incredibly rare that you're not going to find it as an average layperson. Meteorites that are relatively fresh, that's the kind of stuff that's more obvious. There is something called a fossil meteorite. I actually have a couple. And fossil meteorites, they're weathered. They actually look similar to other rocks. But if you cut them open and analyze them, they're still meteorites. We just don't know how long they've been on the ground, and they've been severely weathered. Terribly sorry, I have a cat who wants in. Okay. What else? Meteorites tend to have a little bit of iron in them, except for some of the achondrites, some Martians and lunars and the head group. They typically have very little to no iron in them, so a magnet will not stick to them. Ordinary chondrites, the vast majority of the meteorites that land on Earth, those have some metal in them, and a kitchen magnet will stick to it. Don't get a big old strong neodymium magnet. That'll stick to a whole lot of stuff. A regular small little kitchen magnet, something like this is really good enough. Does it feel heavy for a rock of its size compared to Earth rocks? This is something really important because nickel irons, they're typically between 7 and 8 grams per cubic centimeter. Chondrites usually 3 to 3.6 grams per cubic centimeter. Most of the silicates from Earth's crust that you deal with all the time, they're going to be 2.6 to 2.7 grams per cubic centimeter or less. So if you're holding a rock, and if you've held a bunch of rocks, you know roughly how much a rock is supposed to weigh. But if you're holding something and it just feels a lot heavier than it should be, then that's the thing that we need to look at. All right. All right, here we go. Meteor-wrongs. Okay. Meteor-wrongs, meteorite, get it? I don't know, kids typically get it. Adults may take a little bit longer. So just because it's heavy or has a weird surface or attracts a magnet does not mean it's a meteorite. You have a hematite concretion, which is the bottom right image. It's iron rich, and it can be magnetic. It looks lumpy. It looks weird. It's got kind of that shiny surface, but this is an earth rock. Some volcanic rocks are smooth. Other stuff, like on the right hand side, you have a scoria or a pumice. That looks weird, but there are very, very few meteorites with holes or voids like this. There are a couple of basaltic lunar meteorites and rocks that Apollo brought back that have them. And there's some vesicular diogenites from Vesta, but they're very, very rare. So if you see something with a lot of holes in it like that, it's probably not a meteorite. And then the rest, the other three images on the right-hand side, these are iron slag. Okay, it's a waste product of making iron and steel. It will attract a magnet. It looks shiny, weird, dark surface, but it's literally trash. This is stuff that is skimmed off the top of the molten iron in the smelter and thrown away. These are all impurities from the iron making process, and you know, when you see the stuff, it looks really weird. It doesn't look like an earth rock because it's not. It's industrial waste. So yeah, people have brought that stuff in and said, "Is this a meteorite?" No, it's not. It's trash. So in the before times, actually, let me see if there are any questions. No questions. This is kind of the end of the presentation. We'll go into looking at the actual meteorite in just a minute. So if you have any questions, you can go ahead and bring them up right now. Any questions all about the presentation, anything that we talked about, I can go back over. But I want to tell a little story. So let's see. In the before times, before everything went bad, I took my meteorites out to star parties for the Fort Worth Astronomical Society. So I would be out there with a table and I'd be talking about the meteorites. I'd let people handle them because where else will you be able to actually touch a real space rock? And I had people come up and tell me stories. And I remember several weird ones, but people just don't know a lot about meteors and meteorites, and so they think stuff which is completely different than what it is in reality. And remember, I had someone come and tell me that when they were a kid out on the family farm and who knows where, they had seen a meteor pass overhead, and they said, and I remember how they said it, right over our heads, and then they heard it land in the forest on the edge of the property. And my first thought was, no, it didn't. Because I know about meteors and how high up they are. And I know about how they move and how quickly they move and how they land. And so I kind of had to break it to him because it's a lovely little childhood story. And he said that they heard it land in the forest. They heard it crash, but it was nighttime, and their dad wouldn't let them go out and go look for the meteorite out in the dark forest. That's probably a good thing too. Could have snapped an ankle easily. Nonetheless, I had to tell him that meteors are high up, so they're 50, 75 miles up in the air if it's directly overhead, and when they burn up, it still takes a minute or two, depending on the atmosphere, maybe even less than that, for it to fall down and eventually, land on the surface. And so you wouldn't see a meteorite, and it wouldn't be directly over your head. And that crash in the forest that you heard was probably an armadillo rummaging around through the underbrush. At least that's the way it is in Texas. So it's a nice story, but would you rather have the nice story or would you rather know the truth? And for me, I'd rather know the truth than just have a nice story. So I did have to break it to him that it's not exactly the way things work. But he was very understanding, and it was like, oh well, that's just the way it is. Let's see, any questions? No questions yet. Okay. So, what do we have here? I've got a bunch of meteorites, and I have a couple meteor-wrongs. And in fact, let me do this. Where is it? Where is it? Where is it? Where is it? Oh, there's my box. Here's what I'm going to do. Oh, I have, oops, I have a case of stuff. And one of my cases, I usually take this thing out for star parties. And then I've got my bunch of meteorites in here, and I have some which I've got, which I haven't bothered cataloging yet, and I probably should. I really thought I was going to do that last night, but I just didn't have time. So we're going to switch to, I'm going to do this. I'm actually going to kill that. So we're going to get into looking at actual meteorites. I'm going to put stuff away on the ground, and I could probably use a second table here now. Nonetheless, we'll deal with what we got. Got my catalog that I've finally written out of most of my meteorites, but not. And we're going to go into, we're just going to start looking at what we have. So I have a number, and I've been collecting for a while. Actually, you know what? I really haven't been collecting for a while. I've only been collecting for a couple years. And we're going to switch this over to different camera. Let's see. Let's grab that one. Oh, Yeti. Okay, now do I have audio? I am terribly sorry about that. I don't know why I had audio turned off. Okay. Sorry, I just now looked. All right, here we go. Okay. Okay, I am so sorry about that. All right, let's start over. Okay. So this right here is the very first meteorite that I ever got. Um, and I will correct the video later too. So we'll cut out all that bit. So this is the very first meteorite that I ever bought. I saw it for sale on cloudy nights from a dealer in Canada, and I got hooked. So I thought it was really interesting. I thought it was really, really pretty. And I specifically bought it because I wanted to use it for outreach for the Astronomy Club. I want to be able to take this out to star parties, take this out to events, and have people actually hold a real meteorite in their hands. So this one is Northwest Africa NWA XXXX, which means unclassified. This is not an important rock. So because it's not an important rock, it doesn't get a name. And the reason why we use Northwest Africa NWA is if you go to the Sahara, just second thought, don't do that. Go look at a map of the Sahara and look at all the stuff that's out there. Okay, look at all the valleys, all the little hills. They don't have names because nobody lives out there. Nobody cares. Nobody cares unless it affects them personally. And a hill in the middle of nowhere doesn't affect them, so it doesn't get a name. So instead, we call these things Northwest Africas. And if it's important enough, it gets a number. But pretty much everything found out in the middle of nowhere in Morocco, in Algeria, just out in the desert there, not anywhere near a named geological feature, just out in the desert, it gets Northwest Africa. Now, if it does land near a known geological feature, then it gets that name. So for example, Canyon Diablo is the name of the meteorite that created Barringer Crater or Meteor Crater in Arizona, because Canyon Diablo is the geological feature closest to that location. So here we go. So what you can see here is this dark fusion crust on the outside. It's shiny. You can see it reflecting the light from the light. It's shiny, it's dark, it's smooth. This part right here, this was actually filed off just to see the inside. And it is heavy. So again, this time with audio, if I take a magnet to it, the magnet sticks. And what meteorite hunters typically do is they'll actually glue a string to the magnet so they can hold it very close and they can see just even small amounts of iron. Actually, right here, go. I'm going to put this down for just a second. And, oh dear, where did it go? Oh, there it is. I needed something to point at. Okay. All right, there we go. I need a pin. That little fleck right there, that is a little bit of iron. And I had another one here somewhere, and it rusted. So on contact with air, especially because I touched the thing, and because other people touch this as well. Yeah, it'll just corrode, it'll rust. But you can see these tiny, I don't know how well you can see them. Probably not. Oh, there we go. Now maybe. I can see these little bitty round things that look like chondrules. Not many, but there are a couple. There's right here. There's one right there. And one right there. Under the camera, it's kind of hard to see, but there are two little chondrules there. So this is an ordinary chondrite. But it's neat. And people have asked me if I'm going to cut this thing open and get it polished like some of my others. And I thought about it. And I talked with one of my dealers, and what he said is, I've never cut a meteorite and made it cheaper. That it was always more expensive after, like, the total value of all the slices was always a lot more than the initial rock just alone. So I'm still not going to cut this. This thing just has sentimental value. Just my very first one, so I will keep it. Okay, let's see. All right. Okay. Let's take this one and put it by the side. You know what? Let's do this. I know what I'm gonna do. I've got plenty more. Let's put out a bunch. These all ordinary chondrites. No, that one's not. That one's powerful. Just get a bunch of these out. So I got a bunch of these specifically from Ray, my dealer up in Canada, because I got these for outreach purposes. These I got specifically so that I could take them to locations and I could have people handle them. So in the before times, we actually had I had enough meteorites that I could split the collection in two, where one of our club members, Patrick, actually had some of them, and he could take them to events. So there were star parties that I didn't go to, but that he did. He went to almost all of them. So he would have the meteorites with him, and he was able to show them off. He was able to hand a meteorite to somebody and say, "Here, hold it. Put this in your hand. See what this feels like." Okay, and just this is a meteorite, and you can see the fusion crust on this thing too. This part's broken off. So this part here, the shiny bit here, is where it went through the atmosphere, and then it burst apart into little bitty pieces. And now this part didn't get heated anywhere near as much. So this one doesn't have a fusion crust on it. It's just a bit in piece. And here's like a little piece that got chipped off. So again, no fusion crust. Yeah, no fusion crust in that bit, but there's lots of fusion crust all the way around. I'm going to replace this camera with one of my others for next time. Something which will hold focus a little bit better. But all of these do attract the magnet. So this one just barely. Others a lot more strongly. This one's quite strong in comparison. Especially if you can hold it like this. So definitely magnetic. Little bits of iron. But these things are quite nice. Quite nice just to be able to hand to somebody and say, "This, you're now holding a rock from space." This one's kind of interesting as well. It's got some cracks in it, probably thermal cracks, but we don't know because I haven't cut it open. But this part here, that rough bit, there we go, that rough bit there, it's got a little bit of what looks like fusion crust, maybe, but it's not nearly as smooth as the sides and top are. So this little bit is a chunk, probably it broke in half, maybe in thirds or something, as it was coming in towards the very, very last bit going through the atmosphere. So this crack here, this could be a stress crack. I don't know, because I would have to cut it open and find out. I don't really want to do that. But this is a nice little piece that demonstrates a meteor that basically exploded. It burst apart as it was coming in. And remember, for something like these, again, this one's like a nicely polished bit on one side, just to see what's on the inside. And there's a couple of little iron flecks. If I move it around, you can see one just above that crack. It's a little bitty light bit. Actually, there are two in there. There are several. There are several in there. Oh yeah, there's a bunch of iron flecks in this thing. Let's see. Yep. And what's neat is if I move it around, this one's not terribly apparent. I've got another one I'll bring out, and you can actually feel different amounts of iron through the thing. So again, neat stuff. And these are all Northwest Africa unclassifieds. And Ray actually had these sitting out in his closet. I think he said about 10 or 15 years, just basically untouched, and he just didn't really know what to do with them until I asked, and he goes, "You know what? I've got these." So that's something that I found is very effective. Is I mentioned I get these for outreach. That I'm not the kind of collector who would let these things sit at home. The last year notwithstanding, these things are really meant to be enjoyed, for people to actually look at them, to hold them, to see that this is something that actually came from space. This is not an Earth rock. This is not something that that you see every single day. Well, unless you're in my house. And technically, these are not my meteorites. According to my wife, these belong to my kid. I'm just holding them for him for now. Oh, here we go. So, let's go on. So I have another in Northwest Africa. I actually have 2 slices out of this. That's where my magnets went. I was looking for these magnets, not just that kitchen magnet. All right, here we go. I have a bigger magnet as well, so I don't like that one. I'll use the kitchen magnets. Okay, so here's something cool. This is another Northwest Africa unclassified. And if you look at it, it's got this kind of, what do you call that? Not quite a tortoiseshell pattern. It's kind of that cracking kind of bit, but it's not cracked. It's actually not cracked. It's just kind of, that's just kind of the pattern that it has. This is weathering of the fusion crust. So the black stuff all through here, this is fusion crust material, but the cracks through here, this is weathering. So this rock was actually partially embedded in the ground and just kind of there in the desert for really who knows how long. We don't know. It could have been 50 years, could have been 100 years, could have been longer. It was just out there. Okay, would it be possible to examine those with an X-ray machine to get a look at how the cracks formed? I don't think so, because well, maybe. I'll show you why. This is why. See those cracks? Let's do it this way. Here we go. Can we get it? Can we get it in focus? Focus. Kind of. All right. These big cracks. Let's just do it this way. Hopefully it'll. All right. This shiny stuff here, this is all iron. Okay, here we go. These cracks all through here. These are impact stress cracks. At one time, this rock was part of an asteroid that got hit really, really hard. So this rock got squeezed together and it cracked along these lines. The lighter colored material through here, this is the original material. The darker material all through here, this is metamorphic. It squeezed it so hard that it cracked and melted along these lines. And if I put it at an angle, let's see if we can see the reflection. So this is a neat way to see it too, because I can see it. So you can see the reflection, all those bright spots, that's iron, little flecks of iron. And then we hit this, and we have a totally different type of reflection. Here we're reflecting iron bits. Here, most of the surface is being affected. And then we're reflecting iron again down in this region. Okay? So what we're seeing is a different material. The previous material that was there melted and then re-solidified as something else. And again, this is Northwest Africa unclassified. So I haven't put this in for analysis, but this might be something interesting to do. That this is one of those, it's a chondrite, got a lot of iron in it too. It's got little chondrules, but it's metamorphic. It was in some event in its lifetime that changed it. Also, I not only have this one, but I have another slice. That's a really, really good question, Bart. Excellent timing. Just perfect timing. This is the same rock. Got this from Ray as well. It's the exact same rock. It's a slice from a different part of the rock. But what's interesting about this is, actually, a couple things interesting. You see the cracks all through there again, and you can see the reflection of the light looks different depending on what part you're looking at. And this little black section up here, this is just weird. I'm not even sure what that is, but it's polished up really, really nicely. It reflects very, very nicely all through there. But it's got the cracks, and if I flip it over, so this is the raw side. This is the side that apparently this was a much larger piece that broke up. And if you look at these ridges all through here, this is much, much harder material than the matrix on either side of it. And you can see this crack goes through to that ridge, and you have more cracks through here that go to these ridges, and then you have cracks through here. These cracks go through here. So this rock something happened to this rock. But if you remember the weathering pattern on this guy, let's see if we can get this in focus to see that shiny fusion crust. That's not weathered. It's the exact same rock, but the fusion crust on here isn't nearly as weathered. So that tells me that this rock, which actually fits together something like, let's see where to go. How to do this. Please remember. I think it's something like this. Okay. Yeah, that's about right. Something like this. So here we go. Weathered fusion crust versus non-weathered fusion crust. That's pretty good right there too. Okay. Weathered versus unweathered. So there's like additional slice, probably about that thick or so in between, maybe even more. Seems like it's somewhere about there though. This was partially buried somewhere in here, down in the sand or in the surface of the Sahara. So the part that was buried in the ground, so it came down like this and it was down like this. The part that was buried in the ground did not get weathered. The part that was above the surface got weathered. That tells us a story right there. The story about what happened to this rock. So we now have a bit of a history. Something happened to squeeze this thing together, to crush it, well, maybe not really crush, but squeeze it hard enough to melt the rock. And then when it landed, no one touched it for years. No one knew it was there until somebody found it sitting out in the desert and picked it up. So again, thank you, Bart. Perfect timing. So these are ordinary chondrites. Let's see. Oh, meteoroids. Meteor-wrongs. Meteorites, meteor-wrongs. These meteorites, could these possibly be meteorites? I don't know how that, again, not great focus. I gotta fix this thing. Now it's got a smooth outside. It's got, this weird smooth inside. What is it? This is probably chert. Flint. If I hit it hard enough, I bet I could make a decent tool out of it. I actually have a bunch of chert. And all these, except for this one, these 4 came from my backyard. I've got a bunch of rocks there in my garden. I just picked these out. Actually, no, sorry. These 3 came from the garden. This one is a neat little sample of lanite. And lanite is a pink granite from the Llano, Texas area. It's got these beautiful blue, purple quartz crystals all in it. I don't know how well you can tell that's blue, but it's blue to me. And it's a really, really pretty stone. And this is heavy for an earth rock, and it's very, very dense. And if you go on Highway 6 north of Llano, there's an outcropping there near Babyhead Cemetery. Don't ask me why it's named that. It's Babyhead Cemetery. And if you go look for it, there's this outcropping that Highway 6 cuts right through. And you can get your own samples of lanite right there. That's the only lanite dike that's on publicly accessible land. And you can only find this in Texas. And if you go out there, you need a big old sledgehammer and someone brave to hold a chisel, because I won't. And that's how you have to knock off pieces of lanite to bring home with you if you're a rock hunter. And this is very, very dense. It's heavy for an earth rock, but I'll tell you right now, meteorites feel much, much heavier. So this is a meteor-wrong. And magnets don't stick to it. Oops, let's do that again. Magnets do not stick to it at all. I have a sample of something. It's smooth. It's really smooth, but it's not dark. It's white. It's got a lot of little flecks in it. It's non-magnetic. This is Texas, so this is a limestone. It's just a limestone. But it has some of the features. It's smooth and it's got little flecks in it. So could it be a meteorite? Nah, it's just limestone. And it doesn't stick. This, again, smooth outside, but it's got this weird inclusion in it too. But it's weird. It's weird. It's all smooth. This is a sandstone. This is probably probably some kind of a siltstone with a calcite inclusion onto this. But again, magnet just doesn't stick to it. Then this is, I'm pretty sure this is nice. This is from Colorado. I was there as a kid on vacation and picked this up out of a riverbank. I've had it ever since. It's really pretty. I like it. Magnets don't stick to it. And again, it's smooth. It's dark, but it's not a meteorite. And the reason why I have these, the reason why I bring these out, I have these in the meteorite kit, is so I can, well, again, in the before times, I could go to some place and I could have the real meteorites and the meteor-wrongs, and I could say, pick out which ones are real and which ones are not. Which ones are really the space rocks and which ones are the ones from Earth that I picked up out of my garden. And it's just a way for people to actually visualize and not just visualize, but actually feel and touch that these rocks are from Earth, these rocks are from space, these are the differences between them, and it's just right there in front of them. This focusing thing is driving me nuts. All right, next question. Let's see. Would it possible? Okay, so is it different from an enchanted rock? Yes, the lanite is different from the rock in enchanted rock. Not much different. The granite is pretty similar. But was it a batholith? Yeah, enchanted rock is a big old batholith, and it's a granite. Okay, so enchanted rock was formed when you had basically a bubble of magma flow up under the surface and then cool down and solidify deep underground. The lanite comes from a dike. So it was from a volcanic neck, and there was a crack in the side of the neck, and magma flowed out, a long distance, miles and miles, and then again solidified underground. But it's the color of the crystals that make it lanite. Let's try it again. There we go. So it's those blue, purplish blue crystals. And actually, I think if you go to Llano, there's a bar there and they have a single piece of lanite. It's the world's largest single piece of lanite that they turned into a bar top, and it's really really neat. And I was there with a geology class, oh, ages and ages ago now. All right, I'm going to start putting these away into the box so we can get some others. We'll definitely get these meteor-wrongs out of the way. We'll start looking at some more interesting stuff. Here's the palette site. Let's see how well we can see this. Focus. All right, let's look at the backside. I really wish the focus would be better. There we go. All right. So this is a palisite. This is the stony iron, the olivine crystals. And if you just look at it, it's kind of weird looking. It's got a fusion crust on it, but not quite exactly what you expect. It's got a little bit of shine to it. It's only when you cut it open that you start to see iron and rusty iron in the olivine crystal. So the dark bits are the olivine crystals, or peridot, and the shiny bits and the red bits are the iron. So this is an end piece. This is Siriccio. Yeah, I think this is Siriccio. So this is one that fell in Kenya, I believe. It's this little end piece, and there's tons of these out there. Oh, uh-oh. I have a peridot. I have a little olivine that's actually coming out. Can you see that? Let's see if I do it that way. You see that? That's coming out. So these are not really cemented in there all that tight, especially when it starts rusting. So ideally what I would do with this thing is polish it up really nice and then dip this thing in epoxy. So if this was an epoxy, that would be all sealed and it would look pretty until the epoxy decomposed. Yeah, this bit right there, that's cracking. So remember, iron oxide. Yeah, I just did that. Yeah. Oh, well. I mean, it's mine, so I can do whatever I want with it. Here we go. We have an olivine crystal with a bunch of rust around it. And that's what happens. So if you don't take really super good care of your meteorites, especially the irons, they do just fall apart. Oh, well. It's fine. It really is fine. But if I take the magnet to it again, oh, yeah, this one sticks very, very strongly to it. So if I take these little stick magnets, again, there, that's just sticking right to it right there. But neat thing is, so here's one of the peridot crystals, that orange bit right there. I can't get the magnet to stick to it. It goes to either side, but if I try to get it right on it, it won't do it. It will not stick. It'll just jump over to where there's iron. And if I do the same thing, it's like it's hard to demonstrate it really, but you can see where, oh yeah, that's a bit that just jumped right out. See? It's the iron that's coming out of it. Yep. Hey, this is, I guess, an easy way to clean off my desk, right? So the iron is sticking to that. All right, well, I guess I better take this off, and I'll put this in a baggie or probably in one of the other jewel cases, and that way I'm not losing anything. It's just going to be somewhere else. It won't be part of this one. I don't know why the focus doesn't terribly well. Again, I'm going to have to figure out a different way to do the camera, but that's okay. Questions? Epoxy. Yep. Okay. Keith is asking, is it off Highway 6 or is Highway 16? It's whatever that road is north of Lano. I want to say it's Highway 6. Is it Highway 16? I don't have Google in front of me to find out, but let's see. That was Highway 6. I could be wrong. Let's see. Maps.google.com. And find Lano. Lano, Texas. All right. It is Highway 16. All right, fine. Highway 16. And we're going north. Babyhead Cemetery. All right. You know what? Let's just do this. Because I can't. All right. Here we go. Here's Babyhead Cemetery. Here's Lano. City of Lano. So you go north. And here's Enchanted Rock. Right there. So it's a bit of a distance. Lake Buchanan. So you hit Babyhead Cemetery. Oh, just past Babyhead Cemetery. And I have this marked off. It's satellite view. This is the dike right through here. So this is the surface feature of it. If you zoom in, that's it right there. And if we go to Street View, this is what it looks like. Mind your cactus. But this, all this rock here, this is lanite. And when you come up right to it, you'll see it has beautiful crystals. And there's some on the other side as well. So you just kind of pull over, and you can pull over right over here. We usually just pull over right there and get your sledgehammer and start getting some lanite. All right, let's go back to this view. Okay. Keith, I hope that answered your question. All right. Next. Okay. So I do have a named Northwest Africa. This one is Northwest Africa 10331. This is an H6 chondrite. If we look at it, all that shiny bit, that is all iron. So this, oh, it's just got a lot of iron in it too. Really, all, it's hard to pick up. That right there is iron. All through here, it's just lots of iron, and then little bitty chondrules. Just chondrules all through here, but this has actually quite a bit of iron. And so this is fairly heavy. I forget how much this is. 163.6 grams. So it's heavy for its size. And then if you take a magnet to it, it most definitely sticks. And this one, oh, let's see, where's the other magnet? There we go. Yeah. These stick quite well too. And if I just kind of move the magnet across, I can feel where the iron is, because it wants to stick to the iron and doesn't really want to stick too much to where the silicate material is. And you can see on this side here these elongated specks as well, not just little blobs. So it's all sorts of different shapes and sizes of iron flecks all through here. Now, what's interesting about this is a pristine chondrite. So this is an example of early solar system material. And there are 4 pieces of this rock in the world. So I have one. Tomasz Jakubowski, the guy who found this one in Northwest Africa, he has a piece. And then my friend Ray in Canada has a piece, and a collector friend of his has a piece. So Tomasz actually lent out, I actually talked with him about a year and a half ago. Yeah, I think it was about a year and a half ago now. I talked with him and about this meteorite in particular, and what he said is he had lent out his piece to a grad student in Poland who was writing a thesis on early solar system origins. So I thought that was pretty cool. So my policy has always been, if someone would like to borrow a meteorite for academic purposes, if they would like to use it for research, even take like a little sample off the side and, you know, run it through I don't know, to figure out what it is, that's fine too. So, you know, size is important, and I would have no problem with someone borrowing this and using it for research purposes. Just put a thanks to me on the paper or something like that. And so this one is this one's just a really, really neat piece. It's, you can see it is fairly large, and I actually 3D printed a little cube, a little centimeter cube, so I could show scale. I'm wondering where I put that thing. Right here. Yes, I do. Because scale is a wonderful thing. It tells you just how big stuff is. We printed that thing out too. That one's not for scale. That one's just to hold up meteorites. And I guess, yes, I could have done this before, but I didn't. And I don't see where it is. I know it's in here. I have a little tool thingy that I put all this stuff into. No, I can't find it. It may not be here. And of course it is. There we go. So that is a 1 cubic centimeter cube that I printed because I didn't really want to spend 20 or 30 bucks on a metal one. And the way it's supposed to be is this is T for top. You have front, back, left, right, and ground. So in this case, we have put the top on there. So now you can see, measure out just how big that is. I haven't bothered to do it. So, but that little thing gives you scale on all these. All right, let's go. God, bound to be some interesting stuff in here. All right. Ooh, here we go. Metals. Let's look at some metals. So I have these in plastic for a reason. They're covered in oil because I don't. Oh, they're already starting to rust too. So that's fantastic. All right. They're covered in saran wrap, and they're quite oily. I probably. Oh, I'm probably gonna regret this. That's okay. No, they're fine. This one's fine. It's still in the bag. Oh yeah, this is oily. All right. Let's see if we can do it. Oh, and it's rusting and it's starting to break apart. It's obviously not enough oil. Okay. I'm going to pull it out. And I should probably get a rag or something. Do I have anything I can use? Yes, I have Kleenex. Sorry about the view. I have Kleenex. This will help because I also don't want the oils from my hand going onto there. So here we go. This is, no, I don't remember which one this is. I just don't remember which one this is. I'm terribly sorry. I even have it cataloged somewhere. I have to go look it up. Okay, here we go. Is that beautiful? This is the Widmanstatten pattern that we talked about earlier on iron meteorites. So these are the crystals of kamacite and teosite. Teosite. And it's a differential, slow cooling. And the way you get this is you take the meteorite, you slice it up, you polish it, Really nice. And then you treat it with nitric acid. This pattern comes out. If we turn it on the other side, same pattern. Really is quite pretty. It looks even better, like close up. Actually, can we do that? Yes, we can. Why not? Let's get this one out of the way. Oh, well. I'm getting stuff out of the way. Oh, geez. One magnet sticks to another and makes a big mess. Have to gather up these bits and pieces again. Okay, got those. We see this. Now, I'm going to take another... There we go. All right. So I'm trying to do this in a way that I can... I don't know how well this is going to work. We'll find out. You ready? Let's check this out. All right. It's a little microscope. And I think, yeah, let's flip it to the other side. I think the other side is prettier. This part looks like it's got a little bit of like tooling. Actually, both of them have tooling on them. So these marks that you see, this is actually from the tool used to cut it. Here's what I'm going to do. I'm going to zoom in even more. This is a little bitty digital microscope. Oh, this is not going to work. If you can hear scratching, it's my cat wanting in. I'm not going to let him in. So here we can see some of these crystals. And the diagonal lines going through here, this is the tool mark. But we can see, nonetheless, these crystals and how they're kind of forming. And remember, this is forming in 3 dimensions. So this is a 2-dimensional slice of a 3-dimensional crystal system. So there's stuff that looks like it's overlapping, and where some of these crystals were probably cutting off, like, you can think of them as kind of as needles. So some of them were cutting lengthwise, some were chopping them across, some were being cut at an angle. All these crystals are oriented in different directions that are all they're orthogonal, they're octagonal and orthogonal, and it's just really pretty. It makes a very pretty pattern, especially this crystal orientation. But again, remember, these take millions of years to form. You have to cool this down. It's like, I think the range is like 100 to 10,000 degrees Celsius by 10 million years. So it's a very slow cooling to allow these crystals to form. We cannot replicate this on Earth. Okay, no questions? So I'm going to zoom out just a bit because I want to see them a bit better. Oh, wrong way. There we go. So we're looking deep in, a little bit out, further out now. You can see they're just these very thin crystals. It's very pretty. And it forms this kind of hexagonal pattern, or diamond. I guess it's not really hexagonal. It's like this diamond shaped pattern as they all come together. And they're all overlapping. It's just neat. I think they're quite neat. All right. So this is one type. I swear I have not been mistreating my cat. He's just standing outside my door whining. He has plenty of food. He has more than plenty of food. And he is still complaining. Okay, switch back to this one. Now, look at this one. So this is another iron slice. Its crystals are totally different. I'm gonna have to put these in epoxy. I'm gonna have to clean them with alcohol and then put them in epoxy because they're just starting to rust. Even though they're quite oily, it's a gun oil, keeps them from rusting, but there's just obviously not enough gun oil. So these crystals look totally different. They're much larger. I don't know how well. Yeah, you should be able to see this pretty well. But these are like big blocks. But again, you see this long crystal here, and long crystal this way, and long crystals this way. So they're still very similar. This one probably just has different concentration or different ratios of iron to nickel. So it just looks different. And yeah, the bags are pretty oily. So I'm definitely going to have to do some cleanup once I'm done here, which is fine. I mean, it's part of the deal. So I'm not really worried. It's just I'm kind of more upset that I didn't pay attention to these things as much as I usually did in the past year, and so they've kind of rusted a bit more than I like, and leaving bits and pieces all through here. So yeah, picking up a little bit of iron, a little bit of flecks of iron all here. Yeah. Okay. What are we looking at? Ooh, yes. So head asteroids. Sorry, the head group of meteorites from Vesta. So let's look at that. This is a howardite. Okay. You know what? Let's pull that. Always better to pull that. So the howardites, remember, these are crustal. This is crustal material from Vesta. I'm just going to pull it out. Now, usually, I'll say this, usually I don't have shows that go on this long when I'm showing off the meteorites. I'm usually just showing a couple off and then moving on to something else because the next group of people come in. So this one's got little bitty flecks here. So it looks like it's got a little bit of iron right here, right there, fleck there, fleck there. And if I do, yeah, that's iron. So it's sticking to it just barely. But if I do it over here, there's nothing. That one's got a tiny little bit, and that one's sticking pretty well. So if I let go, it's still sticking. It's trying to stick there. So I'll actually detach. Yeah, it's a little bit of iron, but this is crustal material from Vesta. So this got blown off of an asteroid, eventually landed on the Earth. And this is a Northwest Africa. And you can actually look this up. Northwest Africa, 8362. So if you look it up right now, Northwest Africa, just type in NWA 8362, and you'll find more examples of this one. And let's see what it looks like close up. Why? Because I don't think I have seen it. Here we go. Let's focus. Always in the wrong direction. Here we go. Okay, so we have, this is pretty much going to be, get better focus? Nope. That's probably as good as it's going to get. So we have a little piece of iron right there. And all this stuff, these are not chondrules. If you look at them, these are all like irregular little jagged bits, little dark pieces and jagged bits in a light-colored silicate matrix. And what we see with chondrites is light-colored, often, chondrules in a darker matrix. So then we have these little iron bits. Let's see, where is it? Like that. That's a little piece of iron. That's a little piece of iron. But this one right here, that's not a chondrule. This is wrong color, wrong shape. Even these white bits over here, this white bit here, this is not a chondrule. These are like, you can just think of them as just shattered rocks from, from collisions that made up the crust of Vesta. Stuff which melted, stuff which was broken up and eventually cemented together. This is it looks like it's a breccia. Yeah, maybe not quite. Let's see. What does it say on here? Oh, we got lots of stuff in here. Yeah. This is a fragmental breccia composed of diogenic orthopyroxene, um, cal calcic plagioclase, finely exolved pigeonite, augite, olivine, titanium-bearing chromite, chromium-rich chromite, uh, ilmenite, silica polymorph, triolite, stained nickel-free metal, and some basaltic, eucrite clasts. So yeah, this is a mix of all sorts of stuff, and the iron in here apparently has very very little nickel in it. That would be interesting. Almost all meteoritic iron has nickel. So this, because of its formation, apparently this stuff is nickel-free iron, or nearly nickel-free. And this right here, that just looks like a big old rust spot. And because I say that because of the proximity to the iron. This is just discoloration. And discoloration after it landed on the Earth and was cut open. Not discoloration while it was there, because there's very little oxygen. No oxygen on Vesta. So nothing to discolor. Again, this is howardite. This is crustal material from Vesta. So we've got that, and let's jump off to some more interesting stuff too. Oh, one of my favorites. There we go. This is Northwest Africa 8327. NWA 8327. I'm gonna do this. Let's see, where is it? Yeah, there we go. It's small, but it's got a fusion crust on it, right? Really pretty fusion crust, but it is very small. If I have the centimeter scale next to it, it's not very big at all. Focus. There we go. It's not very large. It's a little bitty fragment. It's only 7.08 grams. What's neat about it is the inside looks totally different. Very, very pretty inside. And it's got lots of little iron flecks. You can see the reflections. And what's neat about this one is we can see just how thick this fusion crust really is if we put it under the microscope. So something kind of interesting is a lot of people really like the way this thing looks on the inside. So people have said, oh, I'd like to make a countertop out of that. That'd be really pretty. Sure would. But remember, you're paying $1 to $2 per gram for this stuff. And that's on the wholesale side. Well, wholesale maybe 50 cents a gram. Retail anywhere from 1 to 5 cents a gram. So, depending on how big, depending on how rare, how pretty. So that's going to be the most expensive countertop in the whole world. There we go. Let's make sure focus is good. There we go. All right. So this is a chondrite. This is an LL5 chondrite. This was found in Algeria in 2006, and there's very, very little weathering on it. It's fairly fresh. But now we can see, because it's a chondrite, we can see chondrules. These round little bits there, that's a chondrule. And the only reason why they look darker is because the background matrix is pretty light colored. All these little things are chondrules, and we see little bitty flecks of metal, and little rusted out bits of metal too. Oh, here we go. Here's some nicer chondrules too, right toward the edge, these dark ones. So you can focus better on it. There we go. So these are some nice chondrules all through here as well. So that one, that's a chondrule. That's a chondrule as well. Just a lot of them all through here too. And let's look at the very edge. So let's find a good place with the fusion crust. Here we go. How's that for the fusion crust? That fusion crust is barely on there. It looks like it's almost painted on. Not at all. It doesn't extend anywhere anything at all into the inside. It's just micrometer thick on the outside. Because as it goes through the atmosphere, all that heat is being taken away. It's being ablated by the material that's blowing off. So the heat never reaches the inside. And you can see that. We have a clast. Let's see, not a clast. We have a chondrules. I know there's some, seen them before. Yeah, chondrules cut in half. And the inside, not even touched. So down here towards the edge. Yeah, right here. There's some chondrules right there that are basically cut in half. And the interior looks fine. More right there. Again, just cut in half. And the heat barely affected anything on the inside. This is a good example right here. The edge right there of how thin that fusion crust is, just right through here. Another chondrule right there, just cut in half. So again, neat, pretty. I like this one. I specifically like to show it off just to show how thin it is. With some of the darker ones, pull out one of the darker ones now. This is an LL6 chondrite, Northwest Africa, 1044. And this one, it's really pretty as well, but it's a very, very dark color. And let's see how much iron's in this thing. There's very, very little. I can feel it. Feel some right there. Yeah, there's very, very little iron in this one. But that's fine. It's an LL6. That's what it is. Let's see, Northwest Africa, 1044. So on the other side, it's just this really pretty brown color. When they're cut fine and polished, they're just really pretty. You can see the fusion crust on the edge. Is barely there. I should probably get this out of the way. Focus. Yeah. And let's put this under the microscope and see some chondrules of this one. Okay, I don't see any other questions. So if you have any questions, let me know. All right. Well, geez, this is going to be hard because this is such a high polish that it's going to be hard to see unless I do something else. Let's see how well this works. Light. There we go. I'm going to kill the light on this one and add in light from the side. Don't see. There we go. Starting to see some stuff. There's a round chondrule right there. Let's put that right in the middle. That round bit right there looks like a chondrule. There's so much in here. This one's just really hard to see. But it's just a really, really pretty rock. I need to look up what an LL6 is specifically. I don't remember off the top of my head. I think, yeah, LL5 is the is Chelyabinsk, isn't it? Let's see, what about this end bit right there? That looks weird, but I'm not sure what that is too. It's still a very pretty rock. Got little flecks of something in there. It's got a bunch of cracks in it too. So this could have been, I don't know. I really don't know. I'll have to go look it up. But we don't need to do that right now. If you want to, go ahead and take a look. Northwest Africa 1044. It's an LL6 chondrite from Morocco. And this was found in 2005. Okay. This one I know. This one's a weird one. Northwest Africa. 4433. Another LL5. Again, This one's got a lot of iron in it. You can see the reflection, the flecks all through there in the light. And it's a slice. It's got fusion crust on there as well. Very thin one. It's just they're just very pretty rocks. This one actually has some decent sized bits of iron. Yeah, I think the side lighting is a little bit better. Maybe. Maybe. Add a little bit of light. Too much. Yeah. So on here, these big flecks here of iron. We actually have an iron vein, which is neat. That bit right there. I didn't even realize that. I don't think I've seen this one under the microscope before. So this has got iron veining too, in addition to all these iron flecks. So I'm wondering what the history is with this one. It's LL5. See, every single rock has a story. Every rock has something to say. And it's us to look at them, to analyze them, and figure out, what is the story? What is it trying to say? What is its history? There you can see the fusion crust. It's kind of hard to see because it's a dark rock, but yeah, right there, you can see the fusion crust on the outside. The part that's a bit down, and then it doesn't come in at all into the interior. The reason why I like these chondrites is they're probably not going to break on you. I hope they don't. What else do I have here? All right, fine. We'll do it this way. This tiny little thing. 2.02 grams out of Tindouf, Algeria. This is Northwest Africa, 11421. Let's get a better view on it. This is not magnetic at all. This is an achondrite from the moon. This is a little piece of highland breccia. It's a piece of a much larger rock. Actually, it's not that big. It's 914 grams for the whole thing. This is just 2 grams of it. So this is a little piece. And this is a moon rock. So we have these big white clasts. Whoops. This big white clast. And the black stuff is the matrix that holds it together. See more of these white clasts along here. So dumping it under the microscope. Oh, let's give it more light. There we go. You can see it. Probably too much light. Let's see. Nope. Nope. No. Yeah, let's leave it. Plenty of light. So the white thing, this is one big clast. We have more of the little white flecks. Here's a clast as well. This is plagioclase and pyroxene mostly. No, this isn't it. No, I'm thinking of something else. This is feldspar. Feldsparic breccia is the proper term. It's got a little red in there, but I don't think that's iron at all. Instead, it's this highland breccia. It's bits and pieces of other rocks just cemented together. So this is light. This is just light silicate stuff from the moon. If you're looking at the moon, this is the bright stuff. The bright stuff in the mountains. This is not the dark stuff of the Maria of the seas on the moon. So, yeah, this is one of my favorite pieces just to use at outreach events. I'm gonna zoom. Let's bring this up. Zoom out. Just see the whole thing a little bit slightly better. Yeah. So I like to bring this one out. It's small, so it just sits in the palm of your hand, especially with little kids. And what I like to do is go to little kids and just take it and just put it in their palm and say, "Can you guess where this is?" Well, I tell the parents to get their cell phones ready to take a picture, and then I tell them this is a moon rock. This is an actual moon rock from the moon. And NASA doesn't let you hold their moon rocks, but I do. Makes me cooler than NASA, doesn't it? It doesn't. Uh, NASA down in Houston at the Space Center actually um, has one of the rocks that Apollo brought back. It's this little triangular thing. You can't even tell what it is anymore. It's black from oxidization, and it's smooth, and it's a little bitty triangle. It's about that big or so, I think, and it's embedded in lucite. So it's in a lucite block, and this just sits just on top of it. And there's another lucite block on top of it with a little crack. So you can just barely stick your hand through, and you can kind of rub it with your finger, and you can say, "I touched a moon rock." Well, I do that every day. So, uh, to me, it wasn't that big of a deal. It was neat, but it wasn't a huge deal, just because I have access to something like this. And this is uncolored. Um, millions of people haven't rubbed their fingers on it, so it's not covered in oils. It's just relatively raw. So, and there are a bunch of pieces of this out there because this thing, because it's a breccia, it's really hard to slice it smooth. It's just going to fragment. So I think marching with this one, it basically just broke open, and they just broke it into slightly smaller pieces to sell. But this is a really neat one. Pretty happy with this one. Um, any questions about it? Remember putting questions or comments in the chat, and I'll get to it eventually. Sorry about the audio earlier. So here we go. So a moon rock. We're gonna go on. What else is there? Northwest Africa 7161. This is a L3 chondrite. This one, again, there's a lot of iron in. Oops. I'm going to drop it down here. I'll kill this because this one has got a bunch of chondrites in it. So it's got iron flecks. Really interested in chondrites like this one. Let's get the focus better. Nope, wrong direction. It's always wrong direction, isn't it? Yeah. So this is a really obvious chondrite right there. It's round. There are chondrites all through here. Every one of these little round things. That's the big one. That's a chondrite right there, that little black one. White ones all through here. These little flecks right there, just all through. There's so many chondrites, just all through there. This is a neat little one right there. More flecks, additional chondrites here. Get out towards the edge, more chondrites. There's a bright one right there. Is that iron? That could be actually iron. Yeah, that one's iron. Whoops, that's not a chondrite. That one's iron. And then that one's iron, and then that one's iron as well. This little one, that one's neat. And if we jump over to other locations, more chondrites. It is just full of chondrites. That's not it. That's a. Oops. Let's get this over. This looks like it could be a chondrite, even though it's not perfectly round. I need to get this thing out of the way so it's not casting a shadow. There we go. Oh, that's much better. So lots of. Ooh, there's a little white one. Let's see, where is it? There we go. There's this white one right there. It's a little chondrite. There's so many of them. It's kind of hard without really analyzing this thing deeply to really tell what all the stuff is. But yeah. Let's see. What is these? I want to turn on this light, see if we can get some reflection. So, okay, there we go. If I turn this up, now we see the irons. We see a little iron deposit and make sure that, yeah, the shiny stuff is all iron. If it ain't shiny and it's round, that's a chondrite. So, where is it? There's that one right there. That one's a chondrite. Geez, there's just a lot of them. So remember, Northwest Africa 7161, and this is an L3 chondrite. You know, I will say this: it's probably been close to a year since I really looked at these. Palisite. Here we go. Yeah, it's my broken one. Semchan. This is from Russia. It's a palisite. Someone, oh man, this thing's just rusting like mad. But yeah, it'll do that. You can see, I'm not going to take it out because it's going to be just You can see it's highly shiny. You can see the crystals of olivine and the metal matrix with a lot of rust on it. There's one, I want to say it's Nanking, but I don't remember off the top of my head. It's a Chinese palisite with a lot of chlorine in it. And it's often sold on eBay from Chinese dealers and as jewelry. So they make pendants out of it and they sell it. The problem is that the chlorine causes it to oxidize incredibly quickly on contact with humidity in the air. And what I mean by incredibly quickly is if you buy a nice little pendant and it's not sealed, you can put it away in your jewelry box and come back 6 months or a year later, and you just have a little bitty pile of peridot crystals and a big pile of rust. So it will oxidize almost completely. So I don't remember if it's Nanking or if it's, I want to say either it's Nanking or it starts with an F, and I just can't remember which one it is. But it should be fairly easy to look up. I guess I can do it now, but yeah, it's you have to be careful with these. And this one, I need to clean it, and the way you clean it is with isopropyl alcohol, high percentage, like 95% isopropyl alcohol in a toothbrush. Clean it as best you can. Cover it in gun oil, and then eventually you're going to want to cover it with epoxy, and that will save it. Yeah, there we are. So that's a palisite, and then nickel iron. So this is nickel iron from Poland, from Morocco, and this one came down about 9,000 years ago, and there are, I think, 11 or 13 craters outside of Poznan in Poland, 9 of which are filled with water. Basically ponds, little round ponds. And back in World War I, the Germans went through and they were surveying it and were trying to figure out where it was and started finding these things. And even now you can go out with a metal detector and find little bits and pieces. So this is a nicely polished, or not polished, this is just a really well cleaned sample of Morocco. And this is iron. This is heavy. So I'm going to drop it down. There. So this is definitely just a big, well, not big. This is how much? 13 grams of iron. And yeah, so you can go out there and so we were going to go to Poland last summer to go visit family, and I had talked with Marcin about going up to Poznan and seeing his little shop there and picking up some pieces, and then going up to Morosco. Bought tickets, I think, November of 19. Yeah, I think about November of 19 for August of 2020. We're going to spend a couple of weeks out there and meet with family and travel around. And nope, we didn't go anywhere. So, yeah, that trip's been postponed. Hopefully, maybe next year we will go. I don't think this year's in the cards, but maybe next year. But I would definitely like to go up to Morosco, and I don't think I would be looking for meteorites myself. I'm not going to bring along my metal detector or borrow one and a shovel and hope for the best, because people do go out there with really sensitive instruments and they look for them. But I'm not going to. So in here you can just see it's not really torn up exactly, but this thing did burst apart in the atmosphere because there are all these fragments. One came down. There are 11 craters. So 11 big pieces came down and probably thousands of small pieces. Irons tend to, if they fragment, they fragment a lot. And the pieces tend to survive. So there's a Russian one too, which is very, very, oh, was it? Oh, I think I have one of them. Well, we'll get to it eventually. So this is Morosco, and 1914 is when it was found, and there's more than a ton of the stuff that's been found, and there's probably a lot more than that still there. You just have to dig it all out. I think Marcin actually has like a big piece. I want to say it's like a couple 100 kilos, and it's one of those things where it's big, it's expensive, but no one can afford to buy it at like market price. So I think he has the University of Poznan actually has it in their collection temporarily. So go back to the heads. This one's actually pretty neat. I like this one. This one is Tierhurt. Tierhurt is a eucrite from Vesta. And so this is volcanic material. And you can see that black stuff, which is the fusion crust. This is a little bitty fragment of the outside. And the white stuff on the inside, the white sugar and brown sugar looking stuff, that is plagioclase and pyroxene. And little crystals of those. It's really, really neat. So the fusion crust, let me turn on this light. There we go. So the fusion crust on here, it's very, very shiny. It's almost like obsidian. And it's also very, very thin. So we're going to zoom way in on this thing because we can. Put this on its side. Roughly. I just want to get that fusion crust. There we go. We're going to see just how close we can zoom in because I really see exactly how close fusion crust is. I'm going to get it way down. All right. Focus. There we go. It looks like glass. It almost is. It looks like it's painted on. That fusion crust is just barely there on the outside, but it doesn't go inside at all. It literally looks painted on. It's not. I mean, we can't replicate this on Earth either. One of my coworkers actually thought he was being funny. He said, "I'm going to go to my backyard and I'm going to pull out, what do you say? I'm going to pull out one of my rocks, just a rock from my garden, take a blowtorch to it, and blacken up the outside, and I'm going to sell it to you as a meteorite." I said, "Well, first, now that I know your plan, I'm never going to buy a meteorite from you. But two, if you take a blowtorch to it, you will heat up the inside. We have really no way of generating the kind of heat that passage through the atmosphere does in a laboratory to very briefly heat the outside without heating the inside. So, yeah, we can't replicate this unless we take a rock and we toss it out into space and have it drop right back down to the Earth. Let's fix that. It's literally the only way we can replicate it. So, try a different area. Yeah, I like to say this looks like white sugar and brown sugar in a burnt caramel. That's what those crystals look like. White sugar, brown sugar, burnt caramel on the outside. And it looks very, very burnt. So this is again, this is a eucrite. This is volcanic material from Vesta. Drop that down. All right, what else do we got? This one is Keneg, Morocco. This is an L5, L6. Yeah, I'll just drop this down here. This is another slice. This is very pretty as well. And lots of chondrites. This is a small, oh yeah. So you see the tool marks and a couple of chondrites through here. Here are some darker chondrites on a white matrix. It's all holding it together. What time is it? It is 10:20. It's not bad for time. I could go on all night long. I'm not going to. Here we see the fusion crust again. And in every one of these cases, we see this fusion crust the same way, where it's so thin, it doesn't extend at all to the inside. Now, I will show you just how big this thing is. It is not very big. Here we go. This is centimeter cube or scale. This is tiny. Okay, it's very, very tiny. But despite that, it survived passage with fusion crust without exploding. What do we got next? Done that one, done that one, done that one. All right, let's go on to, what's this? I don't remember what these are. Oh. Yeah, I'll have to go dig those out. All right. I am going to put this box away. This is my typical travel box that I use, but right now it's going to be a mess, so I'll just put it down. We'll pull out the cases. So I actually use cases for some of this stuff. So I have a nice little display case. It looks like this. It's a nice display case. And this is what we would take out to star parties so we can show it off. And the neat thing about this is everything's in there. It's nice and labeled so you can see what they are and if necessary, take some out to show people. So I've got a couple in here. Let's go to, oh, here we go. This is, focus. All right, fine. Some of these are hard to take out. Oh, because I haven't taped. That would do it. This is, of course, Canyon Diablo. And the reason why 1891 is on there is because 1891 is the year that we realized, that Behringer realized that, hey, this is a meteorite crater. Prior to that, everyone thought it was a volcanic crater. How many volcanic craters are level with the ground like that? Not very many. So this is actually what's called shrapnel. This is a piece of the original meteorite. Was it like 50,000 years ago that landed, something like that, or 5,000 years ago? It's got a 5 in there somewhere. It blew out and tumbled through the air, partially molten, probably, and then landed somewhere in the area as ejecta. So shrapnel is the term we use to describe bits and pieces of the meteorite, of an iron meteorite, that gets blown out from the crater. We also have stuff called tektites, which are a little bit different. Tektites are basically silicates that got melted and blew out, and they're these roundish droplets that landed hundreds or even thousands of miles away from an impact. So shrapnel is remnants of the original meteorite, and tektites are earth rocks that were molten, that were melted and blown away. I've got to fix this. I've just got to fix the focus. I've got to get a different camera to do the focus. This is just not fun. All right, but this is a piece of shrapnel. And again, Canyon Diablo is the name of the geological feature. Barringer Crater is the name of the crater itself. So there's not really much to see with it because it doesn't really have a fusion crust because it melted, it got blown away from the impact, not explode as it came down. Now the interesting thing about Barringer Crater is that that was one of the first ones that we discovered where we realized that just because you have a round crater doesn't mean it was a direct impact from directly overhead. In fact, I think up to 30 degrees or so away from vertical, the crater, from horizontal almost, 60 degrees from vertical, somewhere out there, the crater is going to be round. You really have to get extremely steep angles to get an elongated crater. They're just rare. So when they were looking for this iron meteorite, there's like at the bottom of the crater there's the remnants of the drill site. They were drilling straight down to try to find it, when instead it came in at an angle and it was actually embedded in the wall, or the remnants of the meteorite were embedded in like one of the side walls of the crater, not directly down at the bottom. So remember we talked about mesositerites. Mesositerites, this is Vaca Muerte. This is a mesositerite from Chile. And yes, Vaca Muerte means dead cow. So this is out in the desert where the cows tend not to live too long because there's nothing to eat and there's nothing to drink. But you can see there's a whole lot of iron in this one in a silicon matrix. And this is the back side of it, which I haven't seen for a while. Wow. So this is a piece, and then it was cut and polished so you could see the inside. And again, this is fairly heavy for its size. And magnets definitely do stick to it. We don't typically have any free iron like this anywhere on Earth. It's all rusted over. So just for kicks and grins, I want to shove it under the microscope because I don't think I've actually seen it under the microscope. There we go. So focus. There we go. Lots and lots of iron. And I think there are some Vaca Muertes that have a lot larger pieces of iron. This one just has to be just a really small sample. But yeah, so the idea behind a mesositerite is that it's a iron-rich, like basically an iron core or pieces of an iron core of an asteroid that smashed into relatively slowly into a larger differentiated asteroid with a silicate crust, and then the iron just kind of shattered and broke up and merged with the crust, and over time it turned into a rock. So again, Vaca Muerte. This is a very, very famous mesositerite. All right. Any questions? No questions? No questions. Ask your questions. Ask if I have a weird one, or if one that you know about, I may actually have it. Oh, we talked about fossil. So here we go. No, this is not it. This is Northwest Africa. This is an estenite. Yeah, let's lift this up. A lot of these are just really small samples, and so it's just a matter of. There we go. Yeah, this is an estenite with this weird, like, vein of iron in it. It's a very. This one's very small. This one is very, very small, and it's unclassified, but it's a estenite. Sorry, enstatite. Enstatite. Yeah. Got that vein in it, so very interesting. And then on the other side, it has fusion crust. It's quite dark. It's a little bit weathered, but it's still a fusion crust. It's just that pattern. It's quite weird, quite strange, but interesting. So we got them. But I was going to pull out something else, not this one. I was going to find. There we go. Northwest Africa. This is an EL3 fossil. It looks like a regular rock. I don't see anything special about it on this side. It just looks like a regular rock. And in fact, if I put it on the other side too, I don't really see, that's like leftover fusion crust right there, but it's pretty weathered. So what happens if I take a magnet to it? Bingo. Right there. Magnet sticks to it. That's all I had to do is take the magnet to it. So that's a quick test. Get like a big old neodymium, run it over a big field of rocks out in out in the Sahara, and see what sticks. So this is we call this a fossil because it's weathered to the point where it doesn't look too different from a regular rock. It feels heavier than a regular rock, but it's so small anyway that it's hard to tell. When I say it's small, I want you to see just how small this thing is. Again, 1 centimeter. That's how small this is. And somebody noticed this on the ground and thought, hey, that could be a meteorite. And they picked it up. So it's not just the big stuff, it's the tiny stuff. And again, this is a fossil. So this doesn't mean that it's ancient, like, dinosaur bones or anything. What this means is it's weathered. It no longer has much of a fusion crust, but it's still a meteorite. It's just, we don't know how old it is. All right, looking at other stuff. Where we go? Oh, Guinea. This one is weird. Let me phrase that. This is not weird. It's just that this one is very rare. This one's for Burkina Faso in Africa from 1960. This was an observed fall. So they saw this one come down and then found a bunch of these pieces. This is an H5 chondrite. It's got little flecks of iron. You can see all through there. So the magnet, see, it does attract it. Yep, it sure does. The reason why this one is rare is because, remember what we talked about earlier is finding meteorites in forests? Burkina Faso is forest. It's got a lot of forest. And these were found near a river. But this was a fall. They saw it come down and people went out looking for these rocks. This wasn't a case of, it's, this fell tens of thousands of years ago or 100 years ago and people just happened to find it. No, this was one that was actually observed and people went out to look for it. So it's not very big, but this is one of the very rare African, like, I guess you say tropical African uh, meteorites, stuff that was not found in the Sahara out in the desert. Here we go. This is the one that very, very common one. Sikote Alin. This is an iron from Russia. This was an observed fall in 1947, and there's thousands of these out there. You can go on eBay and pick up bigger pieces than this. But this is an iron meteorite, and just tons and tons and tons. This thing exploded, and just lots of pieces came out. Big pieces, small pieces, a lot. And they have this characteristic kind of flowy pattern to them, if you see. All of them look really similar in that they have this pattern, and it's pretty. It's really neat. But yeah, this is definitely an iron. And if I take, there we go. So it's definitely an iron. Picks it up. But these you can pick up. They're relatively cheap, just because they're so commonplace. There's probably tens of thousands of these things out there. In terms of buying meteorites, let's do this. I'm going to show you my. Oh, that was a mistake. I'm going to show you my mistake, but it ended up being kind of a happy accident, and I'll show you why. I just have to over here, off camera. This. More meteorites. Where is that? Well, I swear I just had it here somewhere. I don't know where it went. Well, that's not a good sign. No, that's actually. Oh, here it is. It was down low. Here we go. Okay. So we go from Sikote Alin, to this tiny little thing, to this thing. So I bought this thing off of eBay. I saw it on auction. I thought, well, that looks interesting. Magnet sticks to it really, really well. And it was advertised as a iron meteorite found in a river, one of several. And the guy didn't know for sure it was a meteorite, but people were telling him, yeah, that could probably be a meteorite. So these are just my little magnets. You can see they're sticking really well to it. And so the pictures weren't terribly great, but it looked suspicious, I should say. It did look suspicious. But okay, magnets want to stick to everything, including other magnets. So my problem right now is I have too many magnets, and they're all trying to stick to each other. Okay. So anyway, I picked this up off of eBay, and this is 1.8 kilos, I believe. Yeah, 1.8 kilos for this thing. Got it for $80. $80 for a meteorite of this size is ridiculously cheap. Suspiciously cheap. Okay, here we go. So, I have a couple questions. Let's see. What makes a weird meteorite? Unusuals. Just something out of place. It doesn't seem normal, I guess. So Martian meteorites are weird. Lunar meteorites are weird. They're just out of place with the rest, but not necessarily in a bad way. It's just that they're just different. And then there are some. Oh, you caught me. I had a few in my head, and now I can't remember any of them. So maybe it'll come back to me. Well, let's go back to that. I have another question. Could you use a metal detector to sort the metal from the non-metal rocks to narrow your search? You probably could. Um, you probably could. Uh, there's enough metal in most of these that they will, unless they're really small. No, actually, that's a good question. I have a metal detector in the garage. I'm not going to go pull it out right now because it has a dead battery, so I'll have to put in a fresh one. But that's something to test. I may do a video on that specifically, is run the metal detector over some of these and see if it picks it up and see how far away I have to be for it to pick up. Oh, that's a good idea. Thank you. I'll add that to the list of videos to do. All right, back to this thing. So, Chinese eBay, 1.8 kilos of iron. And I was suspicious, but I went ahead and got it anyway because, hey, it's only 80 bucks. And if it was, hey, that's a good deal. I could slice it up and sell it. As soon as I got it into my hands, I knew. This is a meteor-wrong. Why? All these little bits here, these are places where the metal pinged off. Okay. Now, there are these things called regoglyphs. Regoglyphs, I forget. Thumbprints. Iron meteorites will have little bitty thumbprints on them. And if I take this one, yeah, the Russian one again, this is what they look like, sort of. It's like this little indentation like this. It's not exactly it, but it looks like a little thumbprint like this here, where it's just kind of in like that, as if it was molten. You just took your thumb and just kind of rubbed it all in there. Real meteorites, real irons sometimes have those. They don't look anything like this. These are pits. They're not. And what those places are is where air whirls will come in. As this passes through the atmosphere, the air will go into little bitty tiny holes, whirl around, etch out that little thumbprint, and then and just create it that way. These don't look like thumbprints. These aren't smooth. Air didn't get into here and smooth this out. If you've ever seen the indentations on river rock, sometimes you get those like a flat rock, and they'll have a little bitty depression, a depression in there. And usually if there are a couple pebbles in that depression, as the water swirls those pebbles around, it'll erode the sides of that little depression and it'll make a little round or round-ish hole in the rock. That's kind of what's happening with meteorites, except just with air, a very hot air. But this one doesn't have it. And what's worse, this area right here, see, it extends out like this. This flat area here, if you look at the reflection, you can see that's relatively flat. This is a piece of Chinese industrial waste iron. This isn't slag. This is iron. This is all iron. But the density is wrong. And there's no nickel on here. I don't know where that kit is. I actually did a nickel test on this thing, and there's almost no nickel in here. Meteoritic iron is going to be 5% up to 50% nickel. Most irons that we have here, most steels, they're like less than 1% of nickel. There's very, very little. So there's almost no nickel in here, which means, one, it's not meteoritic. But that little thing, this little, I call a foot. What this looks like is this fell off long way like this. This do it this way. This fell off of a smelter or something else, and this piece was actually below. It hit, it folded over, and then it dropped down and lay like this, and then cooled. And as industrial waste, this was tossed in a river with a bunch of others, where it got smoothed down, because you can see this is a dark patina on here. It got smoothed down. Some pieces got gouged out. This is a gouge right there that's not smooth. There are pits in here. The pits could have easily been from when it hit the ground. Sometimes if there's a little impurities in there, especially if, like, water or something, it will pop out like this little pit. Like a little bit of iron will just spray out. There are a couple of those. There's lots of little pits on here, but this looks more like, this is Chinese industrial slag. Not slag, Chinese industrial waste. This is waste iron. So as soon as I had this in my hand, I knew this was a meteor-wrong, and I sent the message to the seller, and I said, "This is not a meteorite." I said, "This is why it's not a meteorite," and didn't hear anything back for a couple of days, and I think I got an email. Yeah, I think I got a message back saying, if I gave you a discount, if I returned some of your money, would that be okay? It's like, well, no, because it's not a meteorite. This was advertised as a meteorite, and giving me a discount on junk doesn't make me any more happy. So I said no. I didn't hear anything back. But a week later, I got a message from eBay saying I got a full refund. So there. Now, I didn't send this back because, one, I didn't have a good address for the guy. And two, I'm not going to pay to send 1.8 kilos of waste iron back to China. I mean, this would have cost me, I don't know, this probably would have cost me 40 or 50 bucks just to send this back to him. Like, no, I'm not going to do that. I hope he learned his lesson. Um, but I kind of feel that um, if enough people fall for these kinds of scams, then it's worth it for them to do it. Even if one or two people say, hey, this is wrong, if they have another 10 people who say, yeah, that's fine. I mean, look, the guy sold industrial slag for 80 bucks. Sorry, industrial waste. It's not slag. This is not slag. This isn't skimmed off the top. This is just a chunk of iron that dropped off probably the crucible. So yeah, he sold industrial waste, 1.8 kilos of it for 80 bucks. So if he does that 10, 20 times, and one or two people come back and say, hey, give me my money back, he's still doing really, really well. That's one of the issues with eBay, is you've got scams going on. There are good dealers on eBay. There are dealers that you can trust. You have to find them, and I know a couple. So I can always go ahead and in the chat, or sorry, not in the chat, in the description, I'll go ahead and update. I'll put in some links, and I'll put in some trusted eBay sellers as well. And these are people who actually do this, relatively full time. This is their business. They actually travel and find their own meteorites. They get them analyzed. They do their own slicing, and then they sell them. There's one I know of, Fabian, he lives up in northern Scotland. I think he lives on the northernmost inhabited island in Scotland, and he's an interesting guy. I've talked to him, and the reason why I asked him, why does he live up there? There's almost nothing out there. It turns out his wife is a geologist, and it is a very, very interesting location geologically. So she's up there and she's studying it, and but he likes meteorites, and he's kind of in the same boat that I am, where we both have kids, young kids, that kind of preclude meteorite hunting trips. So he's been kind of on hold for a little bit, and especially for the past year. But he's a good resource. There are also others. I would highly recommend staying away from Chinese dealers. Anything pretty much any, if you see something being shipped from China, I would stay away from it, only because I don't know any reputable dealers out of China. There are good Chinese meteorites, but there's so much scams going on, so many scams going on. It's just really difficult to for a layperson, especially, to figure out which ones are good and which ones are not. Got more African ones. Oh, here we go. Here's something we haven't seen yet. So let's just plop this down on the microscope. Let's get this big iron chunk out of the way. That's always fun to bring out, though. Here we go. See that white inside stuff? And the black fusion crust? Can you guess where this one is? No clues, just guess. All right, fine. This one, we actually saw this one earlier. This is Chelyabinsk. Let's zoom out of it. That. Do it that way. This way, get it back in focus. Yeah, here we go. So this is Chelyabinsk, LL5 chondrite. Look at it again. So the black fusion crust, and this is a pebble which landed probably out in the ice and snow somewhere that someone picked up. So it's very small, but it's got the black fusion crust, and the white stuff is the interior. So we saw an image when we were looking at the Chelyabinsk superbolide. There was an image of a larger piece. There was a pebble just like this one, but there was also a larger piece that was sliced, and you saw a very light colored interior. So we have that on this one. And if I flip it over, it's nicely blackened on the other side too. So it's got a very, very nice fusion crust. And there is interior. So again, here's my finger so you can see just how tiny this piece is. If I use the scale, so this is less than a cubic centimeter, right about a cubic centimeter, roughly. It's going to be quite small. So I have another one. Where can I put that one? Here is it. Oh, but I can't find it. Here it is. I got it. So I actually got this one from my dealer, Ray, in Canada, and this is my other Chelyabinsk, and this is kind of neat. So it was made by a Russian woodworker, and just focus. There we go. It's a fridge magnet. It's a little meteor with a real piece of Chelyabinsk glued into the front, and it's got a little magnet. Actually, had two magnets. One fell off. But this is a little fridge magnet. So he found several pieces and carved these little wooden meteorites and painted them up really pretty. And he sent, I think he sent a couple to Ray, and Ray sent one of these to me. And I thought this was really, really neat. I do not keep this on my fridge. I do keep this with a kit just to show off, just because this is kind of neat because it's a little piece of art made with a meteorite. It's not a ring, it's not jewelry, but it's neat. It's pretty. It's something else. This is basically Russian folk art, and it's a little piece of Chelyabinsk. So when Chelyabinsk exploded, thousands and thousands of these little bitty pebbles just fell everywhere in that area, and because it's the winter, because of February, they landed on the ice and snow. I think one actually fell into like a frozen pond that they then dug out a couple days later. But a lot of these some were larger pieces. I will say there were several larger pieces, but mostly it was these little bitty tiny fragments. And so they exploded, and they're all nice little round. So remember from the video, we saw an explosion and then still burning little pieces coming down. So the explosion split the main mass apart into thousands to tens of thousands of little pieces, which were then still traveling just as fast. And now they get ablated as well. They get rounded just like this thing. And again, 95% of the meteorite gets ablated in its passage. So this thing was significantly bigger. In those last couple of moments, it ablated away and shrunk down. This is all that's left of it. Had a little bit of fusion crust, but the inside is still untouched. It's just neat. Just the idea that the video that we saw, these two little rocks were in there. Somewhere in that explosion, somewhere in that frame, these two little rocks existed. I think it's pretty cool. Let's see. Yes, Chelyabinsk, that was the meteor, the bolide, the super bolide that the explosion knocked out all the windows in Russia. In Chelyabinsk, Russia, not all over Russia. It was quite a bit of damage. So, but fortunately, it was a high air burst. It was not ground level. Had it been ground level, that would have been something completely different. And actually, one of the issues is with stuff like this, especially in a world where you have nuclear powers that are constantly looking out for launches and looking out for nuclear explosions. An exploding meteorite in the atmosphere doesn't look like a nuclear explosion, even though the amount of energy can be comparable or even more. With nuclear weapons, you have something called a double flash. So you have the initial flash, and then followed by a second flash. As I think it has to do with like superheated air and the shockwave going out. I don't remember exactly what it is off the top of my head. I just remember that with nuclear weapons, there's a characteristic double flash, and so we actually have these test treaty monitoring satellites that are constantly looking at the Earth, looking for explosions with this double flash. And typically, what they see is meteorites, meteors exploding in the atmosphere, bolides, and fireballs, and the system can easily differentiate those from a nuclear explosion because there is no double flash. And that double flash is actually very, very rapid. So with Chelyabinsk, we saw several flashes, but it wasn't one big double flash. Vaca Muerte, what else do we have? Chelyabinsk. I have two. These are, I can never remember how to pronounce them. These are more irons from Sweden. These are mono something or other. Let me look at my notes here. Roscoe. Oh, Takahuli. I didn't know. Oh, diagonite there. Okay. No, I don't have it here. Nuts. Oh, Muonion Alusta. Muonion Alusta. And this is, I believe this is from, where was it? Sweden? It's Scandinavia. I don't remember which one. Oh, and that's this first one. Yeah. That's that first one that we saw. And then this is just smaller sample of it. That's gonna be, yeah. And I gotta pull it out again. That's this one that we saw earlier, and it's just yeah, it's just hard to see that pattern right now, and it's so rusty. I'm gonna have to clean it, seriously clean it, and then cover in epoxy. So same one, just a smaller sample of it. And I'm gonna have these magnets back into it in just a moment. But again, we have the issues with rust here, but the crystal patterns really come out. especially on the other side. And if I turn it at an angle, kind of comes out a little bit better. But it's a very, very neat etching pattern. Just not very common. All right, what do we got? I have a lot of these really small ones. Chem. This is provisional chondrite, pre-2000. So this is one of those little tiny things. This one. It's called Chem. And again, someone found this and realized it was a meteorite. It's tiny. This is here. Here's the millimeter scale. Millimeter scale, and yet this is so tiny. But it's magnetic. And someone saw this and thought, well, I'll take a magnet to it, and it picked it right up. So I think this is no longer provisional. I don't remember what the details are on Chem. It's called Chem. So again, in the Sahara, unclassified. Which one is this? Unclassified chondrite, Morocco, 2005. And again, tiny little pieces, but it's got a fusion crust on there. And sticks to a magnet. So I think this is part of a larger one, but nonetheless, it's just really neat that you can find tiny little bits like this and still be able to recognize that it is a it's a meteorite. Here's a piece, Northwest Africa, 869. And again, tiny, but it's got a fusion crust. It's got actually significant fusion crust. It's so tiny, but it's got, actually I have two pieces of it here. So let's get one on the other. That's a fusion crust. It's shiny. It's tiny. And 869 actually has a lot of material to it. It's thought that it was an airburst, so it scattered material just all over the place. But yeah, it is actually being picked up quite easily. Actually, both of them now. Yeah, both pieces. So tiny things like this out in the desert, and yet someone was able to see it and say, hey, that's a meteorite. Here's one, Agildal, an iron meteorite from Morocco. It looks like just a little piece of rust. Oh, but it just jumps right out, even better than the others. It looks literally like a tiny little rust flake. And yet, found out it's got fusion crust on there. That dark stuff is a fusion crust. I wonder what happens if I flip it over what's on the other side. I don't think that's a fusion crust on that side. It's just like soft and rusty. But it is iron, so it is a known iron meteorite. Man, it's been a while since I looked through this stuff. Oh, I've got more fossils. Yeah. So, fossils, again, it's a rock. It just, to me, it just looks like a rock. It's interesting. It's like, okay, well, that's, but it looks like an ordinary rock. But this is a weathered fusion crust on this side. And this is either cut or polished. I think it's just, this is just sliced. It was sliced to see what the inside looks like. And then the other side looks a bit more weathered, but it's got some fusion crust remnant on it as well. Well, Northwest Africa, EL3 fossil. Let's see. I'm not feeling anything. If it's weathered too much and all the iron has become iron oxide, then magnet's not going to do anything. So I'm wondering how they found this one. how they recognized this was a meteorite. And I'm guessing it's going to be from the crust, but just walking over, it's just neat that walking over, they could figure it was a meteorite. Yeah, and the fusion crust doesn't extend anywhere. That darkness doesn't go inside at all. But again, a fossil. Somebody found it and realized it was a meteorite. All right. Next box, something more interesting than just fossils. Here we go. Oh, so this is actually a box that I got. A bunch of, you can call them samples. So, yeah. This is Howardite, Northwest Africa 2060. And again, this is crustal material from Vesta. It's probably not magnetic. Nope, not magnetic at all. So this is just crust. Again, Northwest Africa, Howardite, 2060. Yeah, it's these little bitty pieces. But it's fragments of a much larger one. But this is actually kind of neat, getting these little bitty samples, because you can say, well, I've got this one, I've got this one, I've got this one. Oh, so we're talking about Brenham before, right? Brenham, Palisite, Kansas, 1882. This is a tiny little piece of Brenham. It's not much, but it's there. And I think, yeah, I can't tell if that's black stuff, what that black stuff is. I don't think that black stuff is fusion crust. These are little jewel cases. I don't think that's fusion crust because it had been underground for a while, and it rusted through in some places. So, yeah, these are little. They're called jewel cases, and this is just a open cell foam. But these are really neat because I can keep them in here, and they're relatively safe, and they're small, and they fit into the case. Here we go. So back in 2019, I think April of 2019, so it's been 2 years now. Aqua Zarcas. This is CM2 carbonaceous chondrite from Costa Rica, 2019. Okay, this is a very, very small piece. And what's interesting is that when this one came down, people were saying, if you get a piece of it, smell it, because it's got this, it's the smell of space is what they call it. So fresh carbonaceous meteorites have a particular smell, and I don't think I've ever heard anyone really describe what that smell is. They just say, oh, it's just the smell of space. I was just looking to see if there are any questions or comments. So this is a carbonaceous one, and the reason why, and you can see it's black, but this black isn't fusion crust. This is actually not an end piece. This is an interior piece, and you can see right there that's cut and polished, and you can see some chondrules in it. There are chondrules in this sliced bit, and I don't know how I'm gonna do it. Get them to, there we go. Now it's standing up. You know, I have not seen this one before. This is, it has been a while since I looked through my meteorites. It's been a while since I looked at it from the microscope. So some of these, I'm actually seeing these for the first time through the microscope with you, even though I've had them for a while. So I want to see what chondrules look like in carbonaceous. Oh, that is cool. That is cool. That is really, really neat right there. So we're looking at chondrules with all sorts of hydrocarbons in there. We have amino acids, lipids, lots of stuff, which probably is what gives it that smell. And this is the stuff that formed further out from the asteroid belt, where carbon compounds are able to condense. Closer in, the temperature is just too high, too much. I mean, the temperature from the sun is just too high, and they stay volatile. It's got to be further out. Basically, Jupiter and past for it to be cool enough, cold enough for the carbon compounds to condense out of the medium, the cloud, and form these little chondrules and the rest of it. So this is neat. And it's black. This is a black color, and we're looking at the inside right now. We're not looking at a fusion crust. I don't have an end piece. I don't think this one has any fusion crust on it. I think this is just like a little fragment of it. But yeah, this is the first time I'm actually looking inside of it like this. I haven't done it before. I've looked at the outside. I just didn't bother looking at the cut and realized there was a cut. So we're seeing this together. That's kind of neat. What's Arcus? See if I can. Let me look at the other side. There may be. We're gonna look at this side. Maybe this is. Oh, that could be fusion crust. Right here on the right hand side, that could be a little bit of fusion crust. I don't know. It's hard to tell. Maybe not, because I can see some white flecks through there, so that could just be more chondrules. But that's pretty neat. And on here, yeah, we're looking at chondrules. So there's no fusion crust on this one. We're just looking at chondrules. It's still quite neat. And let me test something. I don't smell anything. Wait. I can smell it. Okay, hold on. I have to basically put it right up to my nostril. It's okay. How am I going to describe the smell? Burnt. It smells burnt. Okay. Like when you're cooking, it smells burnt. I would say like if you're cooking something under high heat on a Teflon frying pan and you don't have any oil in there, or very little oil or butter, no oil, vegetables. You're cooking vegetables on a hot Teflon pan and you forget about them. That's what it smells like. You've forgotten about them and they're burning, they're black, and you have them covered up and you open it up and then you smell that burnt. It's like that, but not exactly. It's I can't they're right. It's the smell of space. I can't tell you exactly what it smells like, but it's burnt. It smells burnt. I haven't smelled this before. I tried to when I first got it, and I thought, I don't really smell anything because it was relatively fresh. I think it was about a month or two old at that point. But it's just been covered up the entire time it's been in the case, and now it smells burnt. That's what it is. They were absolutely right. Yeah, it's the smell of space. There's not really a word to describe it. So there we go. Aquazarcas from Costa Rica. This was a chondrite that fell in 2019, April 2019, and that's neat. That's really neat. Yeah, I like I said, I have not smelled it before. Um, I think when I first got it, I tried to smell it, and I don't think I smelled anything. I think maybe there was like something, but this time it was really noticeable. I just had to shove it almost all the way up my nostril because it's such a tiny piece. Um, But yeah, I could smell it. It smells burnt. Wow. On the plus side, I didn't get any nose hairs on there, so you can't see those on the microscope. That's always nice. Any questions? I'm really sorry we don't have smell-o-vision. I can pass this along. Uh, yeah, that's just a neat smell. I I can say this is the first time I've ever really smelled a meteorite, but this is apparently something that you can do with the carbonaceous chondrites. Um, they're the one rock that has a particular smell, and it's. Okay, I gotta do one more time. One more time. It's, I can't smell it right now. Like, oh, maybe it's it. I don't have a word for that smell. Um, burnt is part of it, but it's also okay. Hang on, let me see. It's not sweet. It's not sour. It's burnt, but it's something else. It's invoking something. Um, dirty socks? No, 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 not really. No, it's burnt and something else. I, I don't know. That's the thing about words. If you don't have a word for something, you you don't have a concept for it. The example that I use is the Greeks didn't have a word for blue for a very long time. In fact, if you read Homer, the way he describes the sea is never blue. The sea is angry. The sea is like a deep wine color. It never described the sky as blue. Um, to the Greeks, the sky was just like was a void. It was just not there. It was just not. I guess you could say it wasn't in their perception almost, but they didn't have a word for the color blue until they started. They had access to Egypt and lapis lazuli, which is a blue mineral that the Egyptians ground up and used to color stuff with. And the idea is that we don't have a word for something until someone can create it. And so, if we look at languages, uh, the first words in most languages um, for colors, it was red, blood, green, plants, um, oranges or ochre, and that's a reddish color for coloring. Browns from dirt, even white. You can make it out of chalk. Blue was almost always one of the last colors to be named because we didn't really have a name for a color until we could create it. So the Egyptians had blue pigments with lapis lazuli, and that's how the word was incorporated, or how the Greeks started using the word is when they started being able to replicate the color. And that's the same thing here, where it's a smell. Burnt is the only word that I know of to describe it, but it doesn't fit exactly. It doesn't smell burnt. It's burnt plus something else, and I don't have a word to describe that something else. It's just that, but it's super neat. Okay, I'll do it one more time and then I'll put it up. We'll go on to something else. We spent quite a bit of time on this one. It's burnt and something else. I I got nothing. It's burnt and something else. So there we are. What else do I have here? I got a Tierhurt. I got another Eucrite. Olivine diogenite. Okay, so this is Northwest Africa. I'm going to go back to the Vestas, the head group. Um, Olivine diogenite, Morocco, 2000. This is Northwest Africa. 1877. Okay, so olivine-rich diogenite. So this is material that came deep out of the mantle on Vesta. And you can see that orange color, which is quite typical of that. Let's see, yeah, and you can see the little crystals all through here, and um, that's the olivine or the peridot crystals. So olivine can survive as a crystal to fairly high temperatures, which is why we see it as the only silicate that's able to survive, that's also dense enough uh, at that crustal and mantle boundary. So anything lighter floats up to the top or up towards the top of the mantle, and the denser stuff, then olivine is really just iron nickel, and that's what goes down to the core. So there's a point where the olivine, one, it's not dense enough to go any further, and two, um, it just kind of melts away, or not melts well. It's heated up to the point where it melts. So we see it in the palladites at that boundary layer. So with this rock, this is higher up in the mantle. The olivine survives just fine, but this is actually a piece of deep mantle material from Vesta, something that we otherwise would really have no way of getting. Um, Especially like on other, let's say like Ceres. Ceres is rather large, um, and it doesn't have any major impacts like what happened to Vesta, that it blew down through the crust into the mantle. So we're kind of lucky that we recognized it for what it is, recognize Vesta for what it is and for the impacts on it, and we're able to get something like this. So Northwest Africa 1877. And this is kind of neat because this is the kind of stuff that I really enjoy. Northwest Africa 1877. That you can show this kind of stuff. And even though this is a tiny, tiny sample, and remember, this is tiny. If I'll put the cap on here, I mean, I don't know if you can even see this on the camera. It's just a little tiny little black thing in the case. But it's there, and it's that simple. So we got the halidites. That's meteorite, Ozarkas. Oh, so many on here. I actually have a bunch from Texas too. So, well, yeah, quite a few from Texas. Let's do this one first. Northwest Africa. This is another example. Go. So this is Northwest Africa 11421. This is the same lunar meteorite, achondrite lunar feldspathic breccia. But this is an end piece, and it's a super thin slice. I don't really even want to take it out of here because it's really, really delicate. But, and also this is like in this neat little plastic case. It's like almost a saran wrap, which is just stronger. So it really holds it in quite nicely. And this is it's a super, super fine slice. There we go. So you can see the white clasts with the black matrix around it. And let's see if we can focus. And actually, let's kill this light. Let's see how well we can see. No, we can't. Am I out of power on this one? Oh no, ran out of power. Oh well. All right, zoom out. Get some more light on this thing. And focus. There we go. See how well this works. Not terribly. All right, so we got it classed. There we go. So now you can see it classed. It's got a crack in it, but you can see the black matrix around it. And just more of these little bits. So this is basically a cemented rock made of bits and pieces of other rocks all together. It was part of an impact on the moon, flew off, went around and around and around for a bit, and eventually landed in West Africa, in Algeria. And the reason why we know this is definitely lunar is because we can compare this to the rocks that Apollo brought back. And when we do, we see, hey, they're the same thing. So Texas meteorites. Travis County, H5 chondrite, Texas, 1889. This is a small fragment. It's a lot less than a cubic centimeter. Let's see, where's my cube? There's my cube. That's a huge cube. That's a tiny little piece. But this one is a known fall. I believe this is a fall. So it was observed to come down, and it's got a little bit of fusion crust on there. Let's get some more light. There we go. This is a little, it's a fairly dark colored rock, but get a little bit more definition out of it right there. So H5 chondrite. I'm going to flip it over, get to the polished side, or semi-polished, I guess. So can't really see. Yeah, I can't really see much, but it's got some chondrules in there, fairly evident. Yep, got a couple chondrules that are showing up. So one of the things that that I like to do more of is find more Texas meteorites, and primarily for outreach. So it's one of those things where, hey, we're in Texas, we can show Texas stuff. I actually have one here somewhere. So this is Travis County. So this was down in Austin. I have, this is, oh man, Davie County. This is an L4 chondrite. And this, that's all that it is right there. So if you look at the text, man, that thing's like, it's smaller than Texas right there. But it's a little bitty piece. I believe this one is magnetic. This is so small if I sneeze, yeah. See, that just jumped right out, right there on the end. If I sneeze, I'm going to lose this thing. I have fragments of meteorites, of some of my bigger meteorites that are bigger than that thing. So this is actually part of a big sample set that I got that I thought was really neat. Lake Murray, Oklahoma. So I was doing a star party at a local library here, and I had someone come by and say, "Hey, we're from Oklahoma, and over in Lake Murray, there's this really big meteorite there at the state park. They've got it at the offices there. You can go up to it and you can touch it." And they thought that was really neat. And I thought, Lake Murray, Lake Murray. I think I got that one. And sure enough, I pulled it out, and it's the same one. So this is one that was found in 1933. I don't remember if this is a fall or if this is just a find. I want to say it was a find, but I don't recall. But this is iron, and again, it's a pretty tiny piece. It's not very big at all. It's like it's breaking up too. It's kind of starting to rust. Oh, but there we go. It picked it up right away. I picked up all three pieces actually. I'm gonna take it off, and I think is that fusion crust? That black stuff? That could easily be fusion crust. Oh, I didn't realize there was a piece of fusion crust on there. Great. Now it's gonna want to jump. Okay, this is so. This is so magnetic that if I take this, I have to take this way away before it drops back down. And I'm still left with like a couple. I just brought it close, and it picked it right up. So, God, it's gonna be okay. I am literally trying to put it down, and it is jumping out. And now I got to figure out how I'm going to get this one down too. So this is a little bitty tiny piece. Go. That's all I got. Nope, one more piece. One more piece. And I have to keep the magnet far away from it, and instead use this thing. And, oh, great! I've magnetized my safety pin probe, so now I was attracted to that. All right, Lake Murray, iron meteorite from Oklahoma. So I have a Martian meteorite as well. My problem is I had it mislabeled. The one I thought was Martian, um, this one, turns out this is definitely a chondrite. How can I tell? Well, those are chondrules. So I have a Martian shergotite. I don't remember which one it is. Now I have to find it. All right. Which won't be fun because I've got a bunch that aren't labeled, which sucks. But that one's not it. I mean, I'm looking for other interesting ones. I've got some from Alaska, Hope Creek, Alaska. These are all really tiny, so I'm trying to find something interesting. Brenham, Howardite, Eucrite. That Diogenite was really nice. A lot of these are just really tiny samples. An olivine Diogenite. No, we looked at this one. No, I haven't. Do I have the second one of these? I do. I have a second one of these too. So I have two 1877 Northwest Africa olivine Diogenites. Sometimes I don't even know what I got. So again, we see that characteristic color, that kind of orange color from this meteorite, and a little bit of dark flecks on there that could easily be the fusion crust. I bet you it's totally non-magnetic. Oh, well, it looks like I was wrong. I was wrong. It's slightly magnetic. There's a little bit of iron in there, even for mantle material. Now let's get that back up. So even for mantle material, there's a tiny little bit of iron in there. Or if that's what this is on top, but I don't know. Okay. I think it's pretty cool. Let's see. Any questions, comments? Go ahead and put them in. You can write them in English. You can write them in Polish. Because I see my mother-in-law is watching now. Yeah, I thought this was my shergotite, but these look a lot more like chondrules to me. Those are most definitely chondrules. So I'm going to have to hunt down which one's my shergotite, unfortunately. Which usually isn't that easy. Yeah. So, what time is it now? It is now 11:30. We've been at this for a while, haven't we? I have a suspicion. All right. I'm going to see if I can find that little shergotite really quick. Because I do want to show that one off. And I'm pretty sure I know which one that is. NWA. So I've got Northwest Africa 12965. If you want to look for it, 12965. I've got Diogenites as well. Let's see, 12965. That's the question. I'm going to have to look through all my notes and see which one that is. It's funny. In the before times, I actually found a good dealer on eBay, and I picked up a bunch of really, really small ones. Just small little meteorites, but I got a number of them. And at our holiday party, our Christmas party in 2019, yeah, I gave them out as door prizes. Those went over quite well. Well, this past year we didn't have any get together over Christmas, and hopefully we're winding down now. And we did have a plan to do a star party tonight, but the clouds kept that from happening. Next week does not look any better, but maybe next month it'll be a little bit nicer. We'll see if we can find some time. I still plan on doing the virtual star parties, So that's still going to happen. It's just a matter of finding the time to do it. And I will be completely honest, I have not had a whole lot of time to do it in the past month. Um, Back in February, we had an issue with freezing here in Texas, and I actually had a pipe burst in my garage. So I had the ceiling came down, so I had to actually replace the ceiling, the drywall, replace the insulation up in the attic, do a whole lot of work, and that process is still continuing. I've actually put up the insulation. I put up a, with help. I had a we put up a new attic staircase. Uh, I put a flooring. I'm doing radiant barrier in there. It will now become a very nice storage space when previously it was completely useless. But um, I oh, I think I found it. Yes, I did. I just found a sugar type. Yep, that is definitely the sugar type. Okay, cool. Well, that was easy, easier than I thought. So yeah, anyway, there's a whole lot of work that I've been putting into the attic just to make it usable, and that's kind of been eating up my time. So I think right now it's 11:35. We're going to look at a Martian Shergotite now. Let's do this view first. So where is it? There we go. Okay, so you got a Martian Shergotite. This is a Mars rock. And if you want to look for it, again, it is, which one is it? Northwest Africa, 12965. Northwest Africa, 19265. And this is a rock from Mars. No chondrules. This is an achondrite. Don't have any specific information on it right this moment, but if you look it up, if you look up Northwest Africa 12965, you can actually read about it. So let's look at it under the microscope, because we're here for, right? Oh wow, hey, that's actually pretty cool. Uh, that's totally different than anything else that I have. Okay, I'm gonna gotta go deeper. Gotta go deeper. Here we go. Right, that's pretty cool. I can't even tell you what we're looking at. I don't know. Oh, I gotta move it this way. Okay, this is like actually up into the microscope now. Let's find out. So here's what I'm gonna do. NWA 1 2, of course, 12965. 965. Let's see if we can find that one. NWA. There we go. This is all right, I'm gonna do this. So we got this going on, and I will switch to this. So here's what we're looking at. I'm actually looking at a website. This is in case you can't see it there, it is the Meteoritical Society, International Society for Meteoritics and Planetary Science, for the Lunar and Planetary Institute. It's kind of neat. And then what you can do is you can actually come in here and you can search for it. So this is Northwest Africa 12965, found in 2019. This is not an observed fall, so it was a find, and 75 grams. So this is a very small one, but it is classified as a Martian Shergotite. Okay, So right up and main mass Kuntz. Yep. So this is Fabian Kuntz. This is the dealer I know from northern Scotland, living in the middle of nowhere. I can't remember what the name of the island is, but it's whatever it is. It's the northernmost island uh, uh, in Scotland. So okay, so what do we have? It single stone without fusion crust, igneous rock with sub ophidic texture, typical grain size, 800. Wow. Yeah, so this is really, really small. Main minerals, strongly zoned pyroxene and maxillinite. Pyroxene has low bake contacts with plagioclase. Opaque minerals are iron oxides and pyrite to. Wow. Okay. Well, that's cool. Let's go back. So that's what we're looking at. We're looking at igneous rock. So this is this is a Martian igneous rock. And that is cool. That is pretty neat. Um, it doesn't smell. I don't think it smells. Not like the carbonaceous chondrite, but it's quite neat. So I actually have labels for these things, and I guess in the next couple days I will be cutting out the labels and labeling all these, so I don't do this again. I've got some others which are also quite interesting. I have some what is it? Some more uh, diogenites and some eucrites. I don't think I have any more howardites. I think that was the big howardite that I had. But nonetheless, I do have some others. Something, yeah, here we go. Here's a eucrite. Um, more chondrites. Chondrites are actually quite common. Um, most of the stuff out there is going to be a chondrite. Um, but I think the Mars sugartype is quite a nice one. Yeah, here we go. So let's get this another eucrite. This is, which one is this? Bottom. I don't. This it? Yep, this is it. This looks like it's it. Maybe not. Yeah, it's just figuring out which ones are which, and honestly, I'll do it later. I'll do it later. We can always do another meteorite show, and especially if I'm going to be going through all these individually and doing individual videos on them, I definitely want to do this. But this is pretty neat. I'm pretty happy I found this one so quickly, and it does look completely different than any other one that I've got. Yeah, it's kind of stuck where it is. Good. But it's pretty neat. I wonder if I can get deeper. No, I don't think I can. It's the nature of this microscope. Um, this is actually it's kind of neat. It's a $20 microscope picked up from Amazon with a little focusing stand and little rotary focuser. It's USB. It plugs right in. The resolution is not fantastic, but you can see detail on this thing. So it's actually not quite bad at all. It's I think it's uh 1280 by 1024. So it's an older chipset, pretty tiny chip actually, but it does the job. We can see details in an igneous rock from Mars. That's that's gonna be pretty cool. I think for this purpose, it's a really neat tool. So it's almost midnight. We've been doing this now for almost 4.5 hours, over 4 hours. Uh, this is fun. I will be working on the videos for individual meteorites as soon as I can and start putting those up. But I think we're going to be done for today. Unless you have any questions, if you can get any of your questions or comments in the next couple of minutes. But other than that, I need to go to bed because I can guarantee you that I will have a 5-year-old knocking at my door at about 6:30 tomorrow morning, and um, I needed more sleep than that. So thank you everyone for joining us. Hope this was entertaining. I hope you saw something that you otherwise wouldn't see, and I also hope that we will soon get back to normal and be able to show some of this stuff in person, let people actually handle meteorites instead of just seeing them virtually this way. But again, my name is Chris Modnitsky, and thank you very much, and have a good night.